the screen, and there is a upward arrow called share screen. You bring your cursor at the bottom of your screen,
and then
there is a green light called share screen. You click
share
on
screen.
that.
Yes.
Yeah, near participants, chat, and then the share screen.
No, this is yeah, share screen.
Yeah.
So now,
yes, this
you can see it.
Yeah, we can see your slides. Yeah,
You can see it.
we can see.
Okay.
It. Yeah, you are ready.
And now what?
Now we see your screen with somebody.
Okay. When I open this,
you have to click on that share the file. Click on the file, then we will see the slides.
Yeah, where is it again now? Here, this
Yes,
is okay.
yes.
Yeah.
Yes.
Okay, so I at the moment you don't need to see it, huh?
Yeah, you can keep it.
So actually, I can keep it now. Then I don't have to search later, huh?
That's
Right. It's only
right.
10 minutes. We can keep it. Yeah.
Okay.
I mean, 5 minutes. It starts at 1:55.
Yeah, in 6 minutes, right?
Right. So you can keep it.
I can keep it, yeah.
Yeah.
So, who is now? He's now joining us at the moment. I heard the Chung's voice.
Yeah, Chung is here. He is online.
Yes,
He said
I'm here. You again.
I don't see you. I see only the Dilip and Jugal.
Yeah, my camera is not working.
So I can hear your voice.
But,
yeah, I see somebody now. I say, another colleague. Yeah. Mm-hmm.
yeah.
Hello, Professor Herzog.
Hello.
Hello, how are you?
Oh, I'm still alive, I would say.
You again. How about Maya?
Oh, my wife is not in such a good condition. She has a hard time to walk. Yeah. She has some problem with the knee and with the legs and everything. So this is not so nice. I'm sorry to say this. Yeah.
But otherwise, he's fine.
And so, Dilip.
Yes.
This is your last day. I mean, before retirement.
Tomorrow is the last day for my
Service
institute.
Yeah.
Oh, I see.
You are in SN only?
Where I am?
SN.
Yeah, I'm still in Essen. Yeah, it's right. I mean, at the moment I cannot travel.
I heard there was a lot of flooding there.
Yeah, not directly in Essen, but nearby. It was really very bad. Yeah, indeed. In Germany, we had so some houses were broken and water came, but not fortunately not in my city. We had also rain, but it was not so terrible. So I got emails from around the world. Oh, yeah, you're still alive. There's a lot of flooding in Germany.
Yeah.
So it was.
One village was swept away completely, it seems. But these floods were not predicted by the Met department.
Excuse me?
The floods were not predicted. It was sudden.
It was predicted, but they did not make a good warning. The warning system was not working very well.
Okay.
Yeah, this is what now they hope to be better in the future. I'm not sure. And how's in India now? The pandemic is better, get going down.
It is in some states. In the southern state of Kerala, it has half of India's COVID cases. One single state is a tiny state.
Oh, really?
Yeah, but in many states it is going down.
For the moment, it comes and goes and comes and goes and comes and goes.
Yeah. So in Maharashtra, which is the state in which Mumbai is, there were 6,000 cases yesterday. Yeah, so it's a lot, but not as compared to what it used to be. It was 2 million at one point.
And do you have what kind of vaccine do you have in India?
AstraZeneca.
AstraZeneca. Oh,
Yeah.
Not so bad, but better than Chinese one, I guess.
Yeah. So I read that this tiny country near Africa called Madagascar, they vaccinated everyone with the Sinovac, the Chinese thing, but they still they are getting COVID, and so the government is vaccinating once again.
Oh yeah. So of course, I'm fully vaccinated. I had 2 times the BioNTech Pfizer vaccine.
Yeah.
And but probably in the fall, late fall, we need another shot. I mean, to refresh.
Yes, I think
I believe.
a third shot. There is some recommendation.
Yeah. For old people.
Pfizer company.
Yeah. The old people, they need some refreshment.
Right. Yeah. So.
Hello.
Good morning.
Hello. Good morning, Martin.
Nice to see you.
Yeah. How are you?
Good.
Oh, sorry. Wait.
Hello, Martin.
Hi. Nice to see you.
Nice to see you.
Martin.
Who is chairing the session?
I am chairing the session.
Okay. All right. Hello, Martin. Hello.
Is Thangavedu here?
Yeah, I'm here.
Okay, great. So, hello. Okay, I'm glad that the speakers are here and the chairs are here.
Yes, I'm
And
here.
I'm sorry, I have been in too many things to do. So, but
I was wondering where has Apurva disappeared.
I just came to the department. Somehow I made it. So, So I think we should be able to start. It's 1:55.
Yes. Yeah. It's time to
Yeah,
start.
maybe. Yeah.
So, Thangavedu, maybe you could start off by and then Martin can take over after that.
Yeah. Welcome everyone for this farewell meeting and the symposium in honor of Professor Dilip Patil, who will be retiring tomorrow from our department. After serving so many years in TIFR, he moved to IIC in 1992. Then he has been a very good teacher with our department. And then, so we thought we will organize something because of the pandemic, we are not able to have any physical meeting. But maybe because of pandemic, we are able to gather a good number of speakers within a very short notice. So everyone is here. A lot of people can attend this online symposium. It's very good. I mean, one of the plus points of this pandemic. I mean, probably only one plus point of the pandemic. So welcome everyone. I mean, I on behalf of the department, I welcome everyone for this symposium and also for the farewell meeting today evening. Tomorrow also there will be a farewell meeting for another colleague and Dilip together, but probably we'll have more today evening. So once again, welcome, and then I will hand over the stage to the chairman of the session. So also good welcome everybody. Here in Germany, it is still good morning, but I guess in India, it's good afternoon, everybody. I'm very happy to announce the first talk, the first speaker of this symposium. It is Jürgen Herzog, and his talk is a short survey on numerical semigroups.
Thank you, Martin, to introduce me. I would like to convey my best wishes and greetings to Dilip, and I can assure him that retirement is not such a bad thing, actually. He has more freedom in the future and a lot of time to prove many more nice theorems, which I hope very much, and we all wait for this. So my lecture is a short survey on numerical semigroups. Dilip also had worked in this direction, had several papers. And so let me begin just with this concept for those who are not so familiar with these ideas. So this is a numerical semigroup is simply an additively closed subset of the non-negative integers which also contains the zero set. And we assume that the greatest common divisors of all the elements in this set is 1. And then when you have a numerical semigroup, any element in such a semigroup can be written as a linear combination of a finite number of elements inside the semigroups. So this means you have this, you have S as a linear combination with non-negative integers, okay? And these are called the generators of the semigroup. And so if you have the generators A1 to AM, then we write S equals A1 to AM and write in such brackets, okay? And the integers, they are called the generators. And here's an example. Oh, sorry, maybe I make a big jump already. Yeah, the smallest number of generators is always a finite number. The smallest such number which generates a numerical semigroup is called the embedding dimension of the semigroup. And here is an example. There is, because of, we assume that, always assume that the greatest common divisor of all the elements in the semigroup is 1, you can easily show that from a certain point you have all the integers inside the semigroup. Then there's a last gap which does not belong to the semigroup. You can see here this example. The generators are 5 and 7, and then, for example, you can get 5 plus 5 is 10, 5 plus 7 is 12, and so on. These are the integers inside the semigroups, and the gaps, they are indicated by these bars. And the last gap you here is 23. And this number, the last gap, is called the Frobenius number. It's a big issue to compute the Frobenius number. You will never find a uniform formula, but in many particular cases, when one has such formulas, or bounds at least, okay? So this is still, and in algebraic terms, this is just for that point from which on you have all the integers. This is just the conductor of the corresponding ring I explained in a moment. So this is, and here, this is such an example generated by 5 and 7. And the Frobenius number is 23. And yeah, the elements which do not belong to S and are greater or equal to 0, so these are the gaps here. So you have a sequence of gaps, and the other elements are the non-gaps, 5, 7, 10, 12, 15, and so on. These are the non-gaps. And yeah, those, oh, sorry. Yeah, in our example, in this example, we have an interesting feature, namely, when you take an integer, non-negative integer, this is a gap if and only if Frobenius number minus a is a non-gap. I go back here, for example, when you take Frobenius number is 23 minus 11, what is this? This is 12, this is a non-gap, it's a gap. Is a non-gap. So the gaps and non-gaps correspond to each other when you take these differences. And if you have this nice property, you call the semigroup symmetric. So this is a very beautiful property of the semigroup, being symmetric. Not all semigroups are symmetric, but the two generated semigroups, this is a classical result and not so easy, not so hard to prove. They are all symmetric. Okay, and there's, from algebraic point of view, there's a reason for that, which I will explain in a moment. So, but of course, these are not, this, for example, this semigroup 4, 5, 6 is also symmetric semigroups. While when you take the semigroup 5, 6, 7, it is not symmetric. Some of them are symmetric, some of them are not symmetric. Yeah. And now we come to the algebra. I promise this, I want to explain what everything means in algebraic terms. And there is a very interesting, nice interpretation for symmetric numerical semigroups. Namely, so what we consider, we attach to any numerical semigroup a ring, a K-algebra actually, a toric K-algebra. So we consider the sub-algebra of the polynomial ring generated by the powers of T. T is, oh, A, so there's a typo, this should be A in S, okay? So all powers of T where A belongs to S. So, for example, when the semigroup is generated by 4 and 5, this would be the subalgebra, and KT generated by T to the power 4 and T to the power 5. This K subalgebra, okay? And this is called the semigroup ring of the numerical semigroup S. And so the question is, this is a nice algebra, of course. It is a subalgebra in the variable T. Yeah, this is a polynomial ring. And then this is one-dimensional Cohn-Macaulay domain. Yeah, because it's a domain, one-dimensional Cohn-Macaulay automatically. And the integral closure, because we assume the GCD of the generators is 1, the integral closure is just KT. And when you, so Cohn-Macaulay in this case is trivial automatically, so to say. But if you can consider this defines in a monomial curve, okay? And when you take the integral closure, no, sorry, the projective hull of this curve, and its coordinate ring, then this coordinate ring, this in general not Cohn-Macaulay. There is a lot of research when it's Cohn-Macaulay, when it's Gorenstein, and so on. But in our case, which I consider here only, we consider only the fine numerical semigroup rings, and they are all one-dimensional Cohn-Macaulay. So Cohn-Macaulay is not an issue. But here comes a result which was shown by Kunz, and it explains what means symmetric. Kunz's theorem says this numerical semigroup is symmetric if and only if this semigroup ring is Gorenstein. So the Gorensteiness is reflected by the symmetry of this. Both are beautiful properties, algebraically, Gorenstein. On the other side, this is symmetry. And now you understand also why a two-generated numerical semigroup is automatically symmetric, because, of course, the defining ideal in that case is just a principal ideal. And, of course, a ring modulo principal ideal is Gorenstein. So that's why. But of course, you can also do it by hand directly, show it must be symmetric. The Kunz's theorem is much more general, actually. It does not consider only numerical semigroup rings. You take any one-dimensional, analytically irreducible ring. So the integral closure is a discrete valuation ring. And then you can talk about the value semigroup of the given one-dimensional ring. And then Kunz's theorem says the value semigroup is symmetric if and only if the ring is Gorenstein. And so when you specialize to numerical semigroups, you have exactly this result here. Okay. Now this is one example where a property of the semigroup has a nice interpretation in terms of algebra. Now the question is, now of course we want to write it as a factoring modulo polynomial ring modulo some ideal, because this is generated by monomials. We call it a toric K algebra, and in that case the defining ideal is always a binomial ideal. Okay, we call this a relation ideal of S, and of course because Ks is of dimension 1, and or what is M? So there's another typo. This should be M here. Okay. Then this ideal IS is of dimension M-1, and is generated by monomials. The relation ideal is an ideal of height M-1. So, for example, when M is 2, as I said before, then the height 1 ideal, so it must be a principal ideal, and then we have this Gorenstein property. So what do we know about this ideal IS? This is not so easy to describe and to understand. We know only in general it is generated by, it's a prime ideal which is generated by binomials. And I believe, I'm not sure, but maybe the first result about this ideal appeared in my dissertation from 1969. At that time I was a student at Louisiana State University. I came with Professor Kunz. He was invited there, and he was so kind to take me as a student. And so I studied this question, and they came to the following conclusion. I say it in simple words what we have. So we take this is a discussion. I told you before, when the ideal is two channeled, we know everything. Now the next case is we assume the semigroup ring is channeled by 3 elements. Okay, and then so you can ask. And the GCD is 1. So this means a multiple of A1 can be expressed by A2 and A3, and the multiple of A2 can be expressed by the other 2. So you get equations like this here. You take the smallest multiple of AI so that you can express it by the other 2 generators. And then, so you have this number Ci, and you have this Rij, which I call Rij. And then you have the following result. First of all, when you have a 3-generated numerical semigroup, the number of generators is at most 3. It can never be bigger than 3. while and it of course can be 2. This is when you have a complete intersection. But if it is not a complete intersection, then the ideal is generated by the 2 minus of this matrix, where the integers Rij, which you see here, they are defined by the equations which I saw before, right? So they are easily to determine. So you take the 2 minus of this matrix, then you get 3 generators in that case. When I wrote this result, I did not know anything about Hilbert-Birch theorem, and actually this is just when you see it in this form, it's a special case of a Hilbert-Birch. Okay. Now, of course, you can ask when is a 3-generated numerical semigroup? When is it symmetric? When is it not symmetric? And I also describe, I also give the condition in my dissertation, but then later, 1976, Delorme completely described all numerical semigroups which are complete intersections. And this is a very nice theorem. The result is this, I say it only in the rough terms. Sorry, where is it here? So S is a complete intersection if and only if S can be obtained from the non-negative integers by a sequence of iterating gluings. So this means, for example, you start with 2 generators, this is always a complete intersection. Okay, I tell you one gluing step. Then, for example, with 5 and 7, this is a complete intersection, as I told you before. So now multiply 5 and 7 with 2, you get generators 10 and 14. Okay, but then there are infinitely many gaps because the GCD is not 1. You take some element outside the gap and add it as a new generator. This is the first gluing step. You can repeat this process, and each time when you do this, we can do it as often as you want. You get a complete intersection. And the interesting fact is all complete intersections are constructed in this way. So this is really a full classification of complete intersections for numerical semigroups. Another question is when these ideals are when they are set theoretic complete intersections. When I came back from United States to Germany, I was a student of Kunz as an assistant. No, I was an assistant at that time, and I showed that all 3-generated numerical semigroups are set theoretic complete intersections. Kunz wrote this proof in his book Commutative Algebra. Yeah, you find it there. Okay. So in general, it is also an interesting question. When are these set? In characteristic P, I think it was shown by Kausik or somebody. Yeah, that they are all complete set theoretic complete intersections, but very rarely they are complete intersections only when they arise as described by Delorme. Then there is another interesting result by Dilip. He studied a special family of numerical semigroups, namely those which are given by an arithmetic sequence. For example, you take 5, 8, 12, and so on. Yeah, but almost. Yeah, this or maybe 5, 7, 9, and so. Yeah, the arithmetic sequence. With one exception is allowed. So one of the members in the arithmetic sequence may not fit to the arithmetic sequence. But in that case, and this implies this result of Dilip includes also my old result of 3-generated semigroup is always of this kind. Okay, and his theorem is a little bit. It's really hard and is a little bit technical. I just can outline what it says. So E is the embedding dimension, then you define P to be E minus 1, and then the number of generators is one of these 3. So there are 3 cases. It can be this number, can be this number, can be this number. And then there are also integers which are not defined here, but they can be computed from the arithmetic of the sequence. So you have a complete description of the number of generators in this much more general case than 3-generated case, and also he gives he really writes down all the equations which define the ideal IS, okay, the relation ideal. And I think this was later by Gimenez, Sengupta, and Srinivasan. When you take the case of an arithmetic sequence, so not this case where one of them may not fit. So really, we take the semigroup is changed by an arithmetic sequence. Then this ideal, which was defined by Patil, can be interpreted as a sum of two determinantal ideals. Again, a very nice description. And this is another. There are many other results. Very interesting is the result when you consider family shifted families of numerical semigroups. There are interesting results, and so it's just a short selection of what is known. But I would say a lot of things are known, but a lot of things are not known. For example, here, maybe I missed this fact here by Brzezinski. In 1975, he showed, so you see, when you two generated semigroup, the number of generators is at most 3. But when you take 4 generated semigroup, the number of generators can be as big as you want. For 4 generated semigroups, there's no limit for the number of generators of the defining ideal. This was shown by Brzezinski by giving a nice family. The only exception is when you have a 4-generated numerical semigroup and the ring is Gorenstein, which means S is symmetric, then the number of generators is either 3, which is a complete intersection, or 5. And it is related, of course, to the Buchsbaum-Eisenbart structure theorem because in that case, the ideas of the prime ideal, the defining idea is a height 3. Gorenstein prime ideal, and by Eisenbart we know this is they are Pfeffians of a certain symmetric matrix. Okay, but this information is nice, but of course Brzezinski didn't know this at that time, but he just proved what is written here. Okay. So this is the only exception, but otherwise the number of generators can be unlimited, even you bound the embedding dimension. Yeah, only for 3 generated is bounded, and for 4 generated and Gorenstein is bounded. Otherwise, it's unlimited. Okay, so much about the relations for the semigroup. Now I want to look at the canonical ideal or the canonical module. So let R be the semigroup ring of S, and then we consider the canonical module of the ring. Because this is a domain, the canonical module is a graded ideal, another typo, I should correct it later. And actually it's a fractionary ideal. And there is a very explicit description of it. Namely, you can say this canonical module is isomorphic, it's generated by so it's a fractionary idea. So you allow also negative powers. And you just take the negative powers of all elements which are gaps. It's a gap. So when you have the sequence of gaps, you take the ideal generated by t to the minus c, where c belongs to the gap. And this is a canonical module. So a very nice description of a canonical module, very explicit description. And some people call this ideal, when you talk about semigroup ideals, just take the exponent. This is called the relative ideal. And another typo, sorry. This should be G of S. Yeah. This is called the canonical ideal of S. Now, we have seen the Frobenius number, but besides the Frobenius numbers, you can consider this is they are called pseudo-Frobenius numbers. These are all elements which are gaps. Such that when you add any element in S which is different from 0, you are inside the ring. Of course, the last gap has this property. So Frobenius number is always there. Other numbers with this property are called pseudo-Frobenius numbers. And they have, again, an algebraic interpretation, namely the cardinality is just the Cohn-Macaulay type of this ring here. So when you look at all pseudo-Frobenius numbers of this semigroup, you get the Cohn-Macaulay type of this ring. And it is explained by the fact, because we know that this canonical ideal is minimally generated by the negative pseudo-Frobenius numbers. And you know, as you know, the number of generators of canonical module is a type of the ring, so no surprise that this you have this relationship. The Frobenius number, the cardinality is a type of the ring. Yeah, then I want to talk about two different versions of generalizing the symmetry or Gorenstein property. One is due to Goto, Takahashi, and Taniguchi, and they call such rings almost Gorenstein. So I say it only for one dimension. You can also make such a definition in higher dimensions. So we take a one-dimensional local ring, and you assume there exists a canonical module. So we don't look at a very exotic ring. So usually there exists a canonical module. And then usually this is another well-known fact. The ring is Gorenstein if and only if the canonical module is isomorphic to R. Now, almost Gorenstein now is this here. You assume that there exists an exact sequence, so you find the generator in omega, and you map the ring, the 1 to this generator, so you get a map from R to omega R, and you may consider the co-kernel. And it is required that the co-kernel is annihilated by the maximal ideal. This means omega R is not so far from the ring, because the difference which is C, so to say, is annihilated by the maximal ideal. Yeah. Gorenstein would mean C is 0, but almost Gorenstein means C need not to be 0, but at least is annihilated by the maximal ideal. So philosophically, it makes sense to call it almost Gorenstein. Yeah, and then there's a nice characterization of almost Gorenstein semigroups, which is due to Nari, and so we take a numerical semigroup and list the Frobenius numbers, which are exactly type many. The largest is a Frobenius number, and so this is a set of Frobenius number, lists them by size, like here. Then almost Gorenstein is equivalent to say that there is a nice symmetry inside in the set of quasi-Frobenius numbers, namely Fi, and so even this plus this is they add up always, the complementary terms add up always to the Frobenius number. There's a nice symmetry property which you can see here. So this is a theorem by Nari. And of course, there is a lot of research for 3-generated, 4-generated semigroups. When are they almost Gorenstein? The 4-generated semigroup is relatively already very complicated. It's a 3-generated semigroup. We have a nice answer. So come back, 3-generated numerical, almost Gorenstein. This was characterized by Nari, Numata, and Watanabe. You look as before at this relation matrix, whose minors are the generators, okay. Then they show that the ring S is almost Gorenstein if either in the first row of the matrix all exponents are 1, or in the second row all exponents are 1. So it has a nice reflection, algebraic reflection again in these terms. For 4-generated, as I said, there is a lot of theory. It is well understood, but rather complicated, okay? And then I want to close with saying, referring to another property of being near to Gorenstein. So we can take any local ring with canonical module omega, a Macaulay ring, of course, and M be a finite generated R module. And then when you have a module M, we define the trace of the module. Just take the sum of all ideals where you map phi, you take the image of M in the ring by a homomorphism from M to R, and take all these ideals as a sum. And this called this a trace of the module. Yeah. And it's easy to prove that the trace of the canonical module describes exactly the non-Gorenstein locus of the ring. And in the paper which I have with Hippie and Stamate, we call a ring. So I should also say the R is Gorenstein if and only if this again typo. I should before I deliver the final version I should type this. This is a trace of omega is R. R is Gorenstein if and only the trace is R. Okay, this is of course omega is R. This is one. Then the trace is also R, but. R is Gorenstein if and only the trace of omega is R. This is an easy statement, okay? And then we say, we call it nearly Gorenstein if M is contained in the if it's almost a ring, it at least contains a maximal ideal. So this means almost Gorenstein, the trace is either R, in which case it's Gorenstein, or the trace is a maximal ideal. So it is as close to R as possible, but not necessarily equal to R, the trace. Then we call it nearly Gorenstein. And because it's semigroup nearly Gorenstein, if the ring is nearly Gorenstein. And again, in the three-generated case, there's a nice characterization of being nearly Gorenstein. Then, in general, the classification is hopeless for classifying all nearly Gorenstein numerical semigroups. But for three-generated, we look again at this relation matrix, and we have the following result. You have these integers Rij, you take this minimum, call it R1, R2, R3, then S is nearly Gorenstein if these three numbers are 1, exactly in this case. And now you can ask, okay, if it is not nearly Gorenstein, so the trace in the one-dimensional ring is an ideal in the one-dimensional ring, and it has a finite length. So if the length is less than or equal to 1 for this factor here, oh, sorry. So this length is always finite in this one-dimensional ring. You could take it as a measure of being Gorenstein or not Gorenstein. So trace less than or equal to, and we call this length the residuum of S, this length. If this is less than or equal to 1, this means the trace contains the maximal ideal. And so this residuum less or equal to 1 means S is almost Gorenstein. And this theorem says when I have a three-generated numerical semigroup, then the residuum is just the product of this R1, R2, R3, which was defined here, right? And then, of course, this implies also this theorem. So the residuum is this here. And here comes a big conjecture. We have it in the three-generated case. We have it in many other cases. All experiments say us the following. We have the number of gaps, and we have the number of non-gaps. And the number of gaps is always greater or equal to the number of non-gaps. This difference here is 0 if and only if it's Gorenstein. Otherwise, it is bigger than 0, right? But we say, what we conjecture is this difference is always less than or equal to the residuum of S. For this, we don't have yet a proof in general, and I ask it as a conjecture. And here are my list of references. And this was my service. Thank you.
So thank you very much for your talk. Are there any questions? There is still a little bit of time before the next talk.
Question. This is Jugal.
Yeah, please.
Jürgen, can we characterize almost Gorenstein in terms of the free resolution of the defining ideal?
You mean in general?
In one-dimensional case.
In the one-dimensional case, I mean, not like in the Gorenstein case, you have symmetry. It's a little bit more complicated. Yeah, this is a little bit more complicated. In embedding dimension 4, you can consider a mapping cone and construct a resolution in this way by using the fact that you have this exact sequence R into omega and M. Yeah, but a nice description. Just looking at the resolution, I think it's not so easy, as far as I remember.
Okay.
I mean, may I ask a question?
Yeah.
Okay. So can anyone say about the last Betty number or the type or something?
Yeah. There are several results. I don't remember the details. There are several results that, for example, for generated and almost Gorenstein, the type is bounded. I don't remember, but there are results in this direction. Okay. But of course, again in small embedding dimension. But this is already quite tricky proofs and results. Yeah, this is true. One can say something.
Thank you.
More questions or remarks? Seems not to be the case. So thank you very much again, Jürgen, for your talk.
Welcome.
And I think we still have a couple of minutes. So let's get the setup and then we start to talk in 2 minutes.
But I have a question now. Can I these slides? Can I do the typos which I found now in the lecture? Can I do repair this and
Absolutely, please. Yeah. Why don't you repair the slides and then send them to me? Thank you.
yeah, I sent it.
Absolutely.
yeah,
After
good.
you repaired them up. Yeah. Thank you. That's fine.
Yeah, this is possible. Yeah, okay. I will send you then the slides with the corrected typos. Yeah. Okay. Thank you.
Absolutely. Thank you. Absolutely. Yeah.
Okay. Jürgen, can you stop the screen sharing?
Yeah. I saw. Yeah. What should I do?
I can do it.
I stop. Huh? No, you stopped.
Okay. Very good.
I can see all participants.
Yes.
Yeah, if you keep it in gallery view, you can see.
Okay, good.
Jugal, are you ready? Do you want to try to share your screen?
Yeah, let
Just to
me
see
try
everything works.
share the screen. Do you see the slides?
More.
Yes.
Now?
Yeah.
Yeah. So, but I cannot see anybody.
That's yeah. In the sidebar, maybe you can see. Are you using iPad or?
No, I'm using desktop.
Okay.
Maybe you can try the standard view.
Exit full screen.
No, on top right, you will have a view button.
Yes.
And then, yeah, no, not the view of your file. I mean the view of the Zoom. In the Zoom window, somewhere you will have the view button. If you click on that, then it shows speaker view, standard view, and things like that.
Yeah, so I should choose what?
No, this view is the view in your, whatever, the PDF window.
Yes.
But Zoom has a view option.
No. Once he puts it in the full screen view, he won't be able to.
Oh, okay. So then you get out of the full screen. Yeah, now you should be able to see that.
The problem with this, we won't be able to see much of.
Okay. Yeah.
This is you have to. You can make it full screen and then you won't be able to see us, but that is fine. I guess you will be able to hear us.
Yeah, maybe I can I start my iPad and then do it?
That's better.
On my desktop, I can see the participants.
That's true. Yeah, that you can.
Okay, let me.
Yes, we could see you.
Is the screen size all right?
Yes, it's fine.
Readable, not a problem. You want to change and then see that That search button, can you close it? On the top bar, that cross mark is there, that you can close. Yeah, can you move lights? Works fine, yes. Martin, are you ready?
Okay, yes. Okay, so we are ready, I hope. So our next speaker this morning is Jugal Verma from the Indian Institute of Science, Indian Institute of Technology in Bombay. And the title of his talk is on the Chern number of good filtrations of ideals. Please.
Thank you, Martin. Can you hear me?
Yes.
Yeah. So, it's a great pleasure to speak on this occasion of my friend Dilip Patil's superannuation from Indian Institute of Science. We'll have more time in the evening to talk about my association with Dilip, but I'm involved in some very urgent exercise in my institute. I want to just say that I have enjoyed over the years discussions with Dilip on many aspects of mathematics. We have written expository papers, and it has always been a pleasure to be in his company, and I'm sure our collaboration will continue and Dilip will remain as young and as active as ever before. So let me begin. The title of my talk is Chern number of good filtration of ideals. Here is the outline. I will recall the concept of I-good filtrations and their examples, some basic notation for Hilbert polynomials of I-good filtrations. I will introduce the normal and tight Hilbert polynomial of ideals, and we use Rees ring and associated graded rings in Hilbert function theory. I will introduce these. Then I will recall some conjectures of Vollmer-Vasconcelos on the Chern number of parameter ideal and normal Chern number of an ideal, and what was done about these conjectures. In the case of Cohen-Macaulay rings, we will see that a result due to Sam Huckba and Tom Marley about the Chern number E1F for I-good filtrations in a Cohen-Macaulay ring implies many results. But then the main focus of the talk is not Cohen-Macaulay rings, but to understand through the Chern number when certain rings are F-rational and Cohen-Macaulay and other things. This is a question of Uniki, which he asked 2 years ago. And I will report some progress towards this question. So here are some examples of I-good filtrations. Take an ideal in a Noetherian ring. A sequence of ideals is called an I filtration if for all m and n, which are integers, in contains in plus 1. So it's a descending sequence of ideals. And if you multiply mth ideal and nth ideal, you get into m plus nth ideal. And I to the power n is contained in the nth ideal in the filtration. These three conditions simply say that when we construct the Rees algebra of this filtration, it's a graded module over Rees algebra of I. Okay. An I filtration is good, called I good, if there is an integer k, so that I n plus k is contained in the nth power of I for every n. There are many I good filtrations. The I-adic filtration is, of course, I good. We say an element is integral over an ideal if it satisfies a monic polynomial of this kind, where the coefficients are coming from the ith power of the ideal. Coefficient of x to the n minus 1 is in I, coefficient of x to the n minus 2 is in I square, and the constant term is in the nth power of I. Then we say the element is integral over the ideal, and set of all elements which are integral is called the integral closure of I. And Rees, back in 1961, proved a remarkable theorem that if you take any Noetherian local ring which is analytically unramified, which means the M-adic completion is reduced. So in that case, the filtration of integral closure of powers of I is I good for all ideals. In fact, this property characterizes analytically unramified local rings. And one can restrict this to one single M primary ideal. Take any M primary ideal, and if I n bar is I good, then the ring is, if and only if the ring is analytically unramified. So if we work in analytically unramified local rings, then we have some control over finite generation of Rees ring of I good filtration. I want to introduce the third important I good filtration, which comes in tight closure theory. Take a Noetherian ring of prime characteristic, and Q is power of P, integral power of P, and take minimal primes of the ring P1, P2, PR, and take their complement, that is called RO. Take an ideal I generated by n elements, A1, A2, AN. We define the qth Frobenius power of I, that is the ideal which is generated by the qth powers of the generators of I. The qth Frobenius power does not depend on the set of generators that you choose. Okay, this is an ideal. The tight closure is the ideal consisting of elements X, so that there exists a C in RO, so that CXQ belongs to the qth Frobenius power for all large Q. Okay, so that's an ideal. It's called tight closure of I. Here is the definition I will use later. An element C, which is occurring in the definition of tight closure, belonging to RO, is called a test element. If whenever X is in I star, then CXQ belongs to qth Frobenius power for all Q and for all ideals. So this element C can be used to test whether some element is in the tight closure of any ideal of the ring. So such elements are called test elements. In good situations, like in excellent rings, test elements always exist. Okay. One can prove this property that I is contained in I star and I star is contained in I bar. So if R is analytically unramified by Rees's theorem, because I n bar is I good, therefore I n star is also I good. So here is an important example, another important example of I good filtration. Okay. With an I good filtration, we can associate a Hilbert function. So take a Noetherian local ring of dimension D. I is an M primary ideal of R. The Hilbert function of an I good filtration is simply defined to be length of R mod nth ideal in the filtration. Okay, so this is generalization of usual definition of Hilbert function of an M primary ideal. How do we know that it is a polynomial? This becomes a polynomial precisely because the filtration is I good. Okay, that's exactly the condition. Now Hilbert polynomial, so there is a Hilbert polynomial associated with this filtration, and we write it in the usual fashion in terms of the binomials. E0f is the multiplicity, and then x plus d minus 1 choose d. Then we write E1f, x plus d minus 2 choose d minus 1, and so on. It's a degree d polynomial. E0f is the multiplicity of the filtration, but it is also the multiplicity of the ideal I. That is easy to prove from definition of I good filtration. And we have the constant term EDF. And we write the coefficients in alternating with the signs alternating. Okay. These are called the Hilbert coefficients of this filtration. When f is I to the n, it is the usual Hilbert polynomial of I. And EIF we will write as EII. And PIX is the Hilbert polynomial of I. If I take the normal filtration, I n bar, then PFX, we write it as PI bar X to borrow the notation from integral closure. And EIF are called normal Hilbert coefficients. Okay, and the polynomial is called normal Hilbert polynomial of I. It was first studied by David Rees in connection with rational singularities. If f is in star, the filtration of tight closure of powers, then we write the Hilbert polynomial as pi star x, and the coefficients are called tight Hilbert coefficients of the ideal I. And we have the tight Hilbert polynomial. Yeah. So in the Hilbert polynomial of a filtration, we have the multiplicity, which is well studied. There are many formulas for the multiplicity. And the multiplicity controls many properties of the ring. For example, whether the ring is regular local ring can be characterized by E0F. E0F can also be used to characterize Cohen-Macaulay property. But the next coefficient E1F, that has been studied extensively in the last 10 years or so. So purpose of my talk is to highlight the role of E1F. So E1F is called Chern number using the terminology that Vasconcelos said. Okay, to study the Hilbert polynomials, we often need three graded algebras. The first is the Ries algebra of I. It's a subring of polynomial ring in one variable. It's a graded ring. The coefficient of t to the n is I sub n. It is simply a set of all polynomials in T, where the coefficient of t to the I is in the ith ideal in the filtration. Then we construct extended Ries algebra of F, where we add negative components, and all negative components are simply the ring. The associated graded ring of F is direct sum of In over In plus 1. When F is In, then the Ries algebras and the extended Ries algebra and graded algebra, they are simply denoted by Ri and R prime I and Gi. If I take a d-dimensional Noetherian local ring and F is an I-good filtration, then the associated graded ring of this filtration is a finitely generated GI module, and that makes it possible to study the Hilbert polynomial. And these are the dimensions of these graded algebras. Dimension of the extended Ries algebra is d plus 1, one more than the dimension of the local ring. Dimension of the associated graded ring is d, and dimension of the Ries ring is d plus 1. An ideal J contained in I1 is called reduction of this filtration if GIN is IN plus 1 for all large n. This is borrowed from the usual notion of reduction of ideals that we find in papers of Northcott and Ries. Here are some results about E1I. So Northcott proved back in 1960 that if you take a Cohen-Macaulay local ring and I is an M primary.
Just give my mobile.
Yeah, is there a question?
Hey. Mobile.
No, so there is no question here. So Northcott proved that E1 of I is bigger than or equal to 0 in a Cohen-Macaulay local ring for any M primary ideal, and equality holds if and only if I is generated by a regular sequence. So therefore, if I take I to be the maximal ideal, and E1 of the maximal ideal is 0, then M is generated by a regular sequence, which means that the ring is a regular local ring. Okay. So vanishing of the Chern number of the maximal ideal characterizes regular local rings. Okay, that's the Northcott result. Vasconcelos wanted to understand Northcott results and other results about E1 in the setting of non-Cohen-Macaulay rings. So these were the conjectures which he proposed in 2008. First is called the negativity conjecture. For any ideal Q generated by a system of parameters, E1Q is strictly less than 0. E1Q is negative if and only if R is not Cohen-Macaulay. Okay, so this is sort of negative result, but with Mandal and Balwant Singh, I proved in 2010 that if R is a d-dimensional Noetherian local ring, J is generated by a system of parameters, then the Chern number is less than or equal to 0. So therefore, the negativity conjecture actually characterizes Cohen-Macaulay ring. It is asking for a characterization of Cohen-Macaulay rings in terms of vanishing of E1Q. That E1Q is 0 if and only if R is a Cohen-Macaulay ring. So that's the negativity conjecture. Partial solutions were obtained by Gezi, J. Hong, and Vasconcelos in 2009, and Mosmi Mandal, Balwant Singh, and me in 2011. The results involve a concept for Noetherian local ring called formally unmixed. A Noetherian local ring is called formally unmixed if for any associated prime of the M-adic completion, the dimension of R completion mod P is dimension of R. Okay. One can construct counterexample to negativity conjecture if the ring is not unmixed. it is easy to construct counterexamples. Okay, so this condition is somehow needed in many characterizations using Hilbert coefficients, that the ring is formally unmixed. Ghezi, Goto, Hong, and Fuong and Vasconcelos, they settled the negativity conjecture in 2010, and they proved the following result. A formally unmixed local ring is Cohen-Macaulay if and only if the Chern number is 0 for some parameter ideal. And in fact, it will become 0 for all parameter ideals once it is 0 for some parameter ideal. Because in a Cohen-Macaulay local ring, the Hilbert function of Q, powers of Q, has no other coefficients but the multiplicity of Q. So that's the result of these 5 authors, which characterizes Cohen-Macaulay rings in terms of vanishing of E1Q for parameter ideals. Yeah. So then it is natural to expect what can you say about the normal Hilbert filtration. Okay, Chern number of normal Hilbert filtration. So here is a result of Akbar and Marley, that suppose you take a d-dimensional Cohen-Macaulay local ring and I is an M primary ideal and F is an I-good filtration and J to be any minimal reduction, then the Chern number is bounded below by sum of lengths of IN over J intersection IN, and equality holds if and only if the associated graded ring of the filtration is Cohen-Macaulay. So there is a lower bound on the Chern number, and if lower bound is achieved, if and only if the associated graded ring is Cohen-Macaulay. Yeah. They also gave an upper bound on the Chern number as in terms of sum of lengths of IN or GIN minus 1, and equality if and only if depth of GF is bigger than or equal to D minus 1. Now you can see that in the case of Cohen-Macaulay ring, if the Chern number vanishes, then the first part says that the length of IN over GIN is actually 0 for all n. And that easily translates into the condition that I sub n is Jn. So my filtration is simply consisting of powers of J, and J is a minimal reduction, so it is a complete intersection. So all the powers become powers of a complete intersection if E1F is 0. So if you apply this on powers of maximal ideal, it simply says that the ring is regular local ring. Yeah. Another corollary, if R is Cohen-Macaulay analytically unidentified local ring and take a M primary ideal, if the normal Chern number is 0, then R is a regular local ring and I is generated by a regular sequence. So Akbar-Marley theorem says that that the IN bar becomes Jn, where J is a complete intersection, and then we use a theorem of Goto, which says that in a Noetherian local ring, which is analytically unramified, if powers of a complete intersection are, if a complete intersection is integrally closed, then the ring is a regular local ring. So vanishing of the normal Hilbert coefficient of an ideal, the Chern number of an ideal, normal Chern number of ideal, characterizes regular local ring. If R is a regular local ring, then certainly it is true for maximal ideal that E1 bar of M is 0. Okay. Now there is a positivity conjecture of Vasconcelos. He proposed at the same time in 2008. For any M primary ideal of an analytical unidentified local ring, E1 bar of I is bigger than or equal to 0. Okay. This is unlike E1 of a parameter ideal being less than or equal to 0. But if I go to a normal Hilbert coefficient in an analytical unidentified local ring, then it is always non-negative. Okay. Now this with Mosmi Mandal, Balwant Singh, we settled this conjecture in many cases. For example, 2-dimensional complete local domains, analytically unidentified local ring, so that there is a Cohen-Macaulay local ring containing R and S mod R has finite length that amounts to having a Cohen-Macaulayfication. The integral closure of R is a finite Cohen-Macaulay R module. So in these cases, we proved this conjecture, but Mandal, Hong, and Goto then settled the positivity conjecture for all formally unmixed, analytically unidentified local rings. So formally unmixed now becomes sort of a necessary condition for characterization of properties of local rings, which are implied by the vanishing of the Chern number. Okay, now the last few minutes, let me go to some new results. And here we are seeking characterizations of local rings using the vanishing of the Chern number of tight closure filtration. So first I recall a Newtonian ring R of prime characteristic is called weakly F regular if all ideals of R are tightly closed. If the localization is weakly regular for all prime ideals, then the ring is called F regular. Regular local rings, polynomial rings over a field, direct cements of F regular rings, they are all F regular. This was proved by Hochster and Hunicke in their paper in, I think, 1987 or 88. Okay, so there are lots of F regular rings. There is a bigger class which is also very interesting. It is called the class of F rational rings. An ideal I of a Newtonian ring is called parameter ideal if it can be generated by height I elements. So in Brunn-Herzog, we find they want to call it an ideal of principal class, but it is also called a parameter ideal. So it requires an ideal by Krull's theorem requires at least height I elements, but if it is generated by height I elements, then we call it a parameter ideal. A Newtonian ring R is called F rational if all parameter ideals are tightly closed. So of course, F regular rings are F rational because their all ideals are tightly closed. If R is a homomorphic image of a Cohen-Macaulay ring, that's not a very restrictive condition. One can prove that all excellent rings are homomorphic images of Cohen-Macaulay rings. In this situation, if the ring is F rational, then it is actually normal and it is Cohen-Macaulay. And the amadic completion is also F rational. The localizations are also F rational. Okay, so excellent F rational rings have lots of nice properties. They are normal, Cohen-Macaulay. The completion is well behaved. Localizations are well behaved. In fact, later on, it turned out that F rational rings are counterparts of rational singularities in characteristic 0. And they have many properties common with rational singularities. You will see in one example here. Take a field of prime characteristic and take polynomial ring in 3 variables. Look at this quotient ring, S mod x square plus y square plus z square. This is always F rational if P is greater than equal to 3. Okay. It follows from one result that a Gorenstein ring, if it is F rational, is actually F regular. Okay. If you take S mod x square minus y cube minus z7, one can prove it is not F rational. So one is curious to know what is the property of the exponents which is responsible for F rationality. Okay, here is another result. Take x squared minus y cube minus z5. This is F rational in large characteristic, P bigger than equal to 11. Now, this is the result of Watanabe and Yoshida, I think. If P is bigger than equal to 11 and the sum of reciprocals of the exponents, xa, yb plus zc, it is bigger than 1, then the quotient ring is F rational. Okay. In fact, it will become F regular because Gorenstein F rational rings are actually F regular. Okay. Now let me come back to the vanishing property of even star of Q. So as I said, if I take the filtration of the integral closure of powers of Q, that is a Q good filtration. One can associate a Hilbert polynomial with Q and star. And in the setting of Cohen-Macaulay rings, with Kriti Goel and Vivek Mukundan, we proved that if you take Cohen-Macaulay analytically unramified local ring of prime characteristic and I generated by system parameters, then the tight Chern number vanishes if and only if R is a F rational local ring. Okay. Yeah. So this is a sort of continuing philosophy that vanishing of the Chern number gives a nice property of given local ring. Yeah. Here is a question that Hunicke asked about 2-3 years ago. Take a formally unmixed local Newtonian ring, Q generated by system parameters. Is it true that even star Q equal to 0 if and only if R is F rational? Yeah. So this is in line, it is in accordance with the previous results about vanishing of Chern number when the ring was just assumed to be formally unmixed. So his question is, move away from Cohen-Macaulay rings in the setting of formally unmixed local Newtonian ring. Can we characterize F rational rings in terms of vanishing of the tight Chern number? And this is a result that is still being written. We can construct a complete local domain of dimension 2 that is not F rational, but there is a m primary parameter ideal so that even star q is 0. Okay, so therefore Unique's question has a negative answer in dimension 2, even for complete local domain. So something deeper is going on here. Here is an example. Take this ring x4 x cube y xy cube y4. This is the local ring of Macaulay curve. Its integral closure is generated by all monomials of degree 4 in x and y, and that is Cohen-Macaulay, and it is even F regular. And then one can let me, because I don't think I have time. So let me go to. I'll skip this calculation. So this calculation says that the ring which is obtained by completing the local ring of Macaulay curve at the origin is a counterexample to Unique's question. But that ring is not Cohen-Macaulay, of course, a dimension 2. So we want to characterize when F-rationality can be implied by vanishing of the tight chain number. So here is the result which we have just written out. It is joint with Saint-Pierre Dubé and Pham Hung Quai from Hanoi. So the result says that if you take an excellent reduced equidimensional local ring of prime characteristic and dimension is at least 2, take test elements. Rather than taking arbitrary system parameters, take a system parameters generated by test elements. Such ideals exist if the given local ring is F-rational on the punctured spectrum. There are many examples of such kind where there is a system parameters which is generated by test elements. Suppose I have such a system parameters, then R is F-rational if and only even star Q is 0 and depth is at least 2. What goes wrong in the earlier example that it was a depth 1 ring. And so we were not able to, we had even star of Q was 0, but R was not even rational. I mean, not even Cohen-Macaulay. F-rational rings, excellent F-rational rings have to be Cohen-Macaulay. Okay, so there is a depth condition in addition to even star of Q. If I assume that depth is at least 2 and even star Q, then R is F-rational, and this is a necessary and sufficient condition for F-rationality. This result makes use of a crucial result proved by Lin Chuan Ma and Pham Hung Quai, which let me just flash this result. It says that length of Q star over Q can be written in terms of the local cohomology modules. It is sum of D choose I, length of HIMR plus length of what is called the tight closure of the 0 submodule in the top local cohomology module. Okay. This result will soon appear, but using this result, we are able to prove the characterization of F-rationality in terms of even star Q and depth of R is bigger than equal. So I guess my time is over and I will stop presenting. Yeah, thank you very much.
Thank you for your talk. Are there any questions or remarks? No questions? Everything clear? Oh, okay, so thank you very much again.
Thank you. Thank you very much.
And we will continue in a few minutes, but first we have to set up the technology for the next talk.
So we start after 3 minutes approximately, right?
Yes.
Okay.
Yeah, 3. Indranath, you want to share your screen and check?
Visible, right? Clearly?
Yes, everything fine.
Yeah, and this size is good enough, I believe.
Yeah.
Okay.
Are you planning to write anything? Or?
No, not really. I will, but these are handwritten. I'm just going to sort of.
Yeah. Okay. Thanks.
So are we expecting anybody to specifically show up for Indranat's talk, or can we continue? I think we can continue, right? Oops. Okay, so I think we can continue now. So our next speaker and the last speaker before the break, is Indranath Sengupta, and he's from IIT Gandhinagar. And his topic is some results on numerical semigroup rings. Please.
Martin, I think there is a question to Professor Herzog. If you see the chat box, maybe.
Yes, but it was not really complete. Now it is complete. Okay. I think maybe we can answer this question after your talk.
Okay, fine. Okay, so I'm clearly audible, right?
Yes.
Okay. So thank you so much, Martin, for this introduction, and thank you very much to the committee for inviting me, especially to Apurva. I mean, arranging this in such a short time is something extraordinary, I must say that. Okay, so this is the topic, and you have already heard a talk from Professor Herzog, who is a known expert on this in this area. So really speaking, probably you would find it a repetition, but just some new thoughts which has occurred in recent years. I would like to share that with you, but I will start with these three articles by Professor Patil, and which is kind of my entry point to this area of numerical semigroups and numerical semigroup rings. And I joined IISc Bangalore in 1994, and when he kindly agreed to be my PhD supervisor, and I worked with him. And these are the three sources which kind of gave me the necessary background. So these are and you will see that I will talk about some results. Of course, it's impossible to say everything he has done. There are lots of things, lots of results he has proved. Just, I'll be a little choosy, and I will just also say that some new thoughts, as I've already mentioned. Okay, so this is some basics of numerical semigroups. You have already heard from Professor Herzog. He has already mentioned that. So interestingly, I'm just sticking to the, mostly I'm sticking to the notations that Patil used in his papers. So this n is the set of natural numbers together with 0. And we are using this gamma for the numerical semigroup, which is an additive submonoid of n such that it is finitely complemented. You know, this is the definition of a numerical semigroup. And you can in fact prove these with not much difficulty, that actually you can prove that every numerical semigroup has a unique minimal generating set. And then the GCD of these elements is 1, as you have already heard in Professor Herzog's talk. And every non-trivial submonoid of n is isomorphic to a unique numerical semigroup. So these are in fact very nice kind of results. And once you know the definition, they follow with a little bit of effort. And now comes this definition of the conductor and the Frobenius number. So the GCD1 condition automatically makes it finitely complemented, etc. And therefore, you will see that there will be a stage from that onwards, everything will be inside the semigroup gamma, and that stage, that number is what we call the conductor, usually denoted by C. And the previous one, which is obviously not there in gamma, that is called the Frobenius. And this is, of course, still a very hard thing that like people make various efforts to give bounds, to give calculations for Frobenius. There are also the computer scientists interested in this problem and things like that. Okay. Now, and also what Professor Herzog mentioned is that the result by Kuhns on the connecting the Gorenstein monomial curves with the symmetric numerical semigroup. There, of course, the conductor ideal, these things play a very important role when you are showing that the value semigroup is actually symmetric. Okay. And now again, as I have said, I am using Professor Patil's notations. So this was the notation that he used in his paper, that this is delta. So gamma, remember, gamma is the numerical semigroup and gamma plus is the set without 0. And then look at those alpha non-negative integers such that when you add every element of gamma plus to this, then it lands inside gamma. Okay, so this set is this set delta, and then you remove the elements of, oops, I'm sorry, this I meant gamma. Okay, so you remove the elements of gamma. Obviously, if you just take these elements of gamma, they would obviously belong to, when you add them with the elements of gamma plus, they would belong to gamma. So if you just throw away the elements of gamma, okay, then what you get is this set is what is called the pseudo-Frobenius. In fact, in the previous talk, it was denoted by PF of S. So this is our pseudo-Frobenius. Now this set also happens to be very, very interesting, especially from the standpoint that I'm going to talk about, or what Professor Patil has done. And a few more notations. And then if I assume that this is a generating set with GCD1, okay, and if you, in fact, it's better to take them to be minimal and things like that to avoid redundancy. And then the smallest non-zero element, you call that the multiplicity of the numerical semigroup. And then, well, here I am just saying the Aperi set with respect to the multiplicity, but it is not necessary. You can in fact define the Aperi set with respect to any non-zero element of the numerical semigroup. That goes perfectly all right. But let us do it only for n for the time being, because that serves the purpose. And later on, I will make a comment. Okay, so this is how we denote this set by the s suffix n. Remember, m is the smallest element. So here we are taking that to be m0, the smallest element in the generating set. Okay, and then this is the definition, which is set of all those elements such that, oops, sorry, I mean the set of all those gamma, such that x minus gamma is not in n. So there's a typo. Okay, and this is precisely the set of m0 non-negative integers, or rather m non-negative integers, giving for each I between 0 to m minus 1, the smallest integer in gamma congruent to I modulo m. I mean, there is some, I think I better correct it immediately. Because I have already M, and this is also, yeah. Okay, yeah. Now comes this very important theorem from this paper of which was published in 1990. I showed you those three in the list. First is thesis and then a couple of papers. So where they described this set explicitly for an almost arithmetic sequence. You have already heard what an almost arithmetic sequence is. That means this is a string of, this is of E integers such that all but one form an arithmetic progression. And interesting enough, actually, this is very sorry, I'm not able to recall the exact year, but this calculation of Aperi set, understanding the Aperi set actually holds the key to various results. It's a very important thing to understand a numerical semigroup. Well, there are various approaches. Well, I would not say various. There are definitely some other approaches, and one is by the continued fractions by Alphonsine. I will add the exact details later on before I share the slides. So the point is that there are some ways to understand. Okay, I mean, it's mostly a Diophantine problem. You can understand that you are trying to find out the smallest ones congruent to I modulo m, and there are ways to try that. And once you know the Aperi set, you know a lot of things. In fact, I will be telling you what all they did in this paper and in the subsequent papers. You can understand that it's mostly coming from the Aperi set. Okay. Okay. So now let me quickly tell you what all were actually proved. I mean, at least some of the results, as I've already said, that assuming that K is a field of characteristic 0, let O be a curve in the affine E space over K with the relation ideal P. Given E, are there upper bounds on the minimal number of generators of the derivation module over K and the minimal number of generators of the relation ideal P? As I have said, I am using exactly Patil's notation. So this is how they have written in the paper. I am sticking to that. So now this is, and also this is the comment they have made, that they observed a striking similarity in several cases between the behaviors of mu of dark O and mu of P. And indeed, so it still actually is very, very interesting. You will see from another perspective also. So here, these are the immediate observations that when your E is 1, remember E is the embedding dimension, because if we assume that there are exactly E integers, they minimally generated the numerical semigroup, etc. So this E is what is called the embedding dimension, and M or M0 is the multiplicity. Okay. Now, if the embedding dimension is 1, then it is, of course, you can immediately see that what would be your mu P and mu of dark O. Now, the interesting thing starts when you have E equal to 2. Then you can again prove that mu P is 1, but mu of dark O is at most 2. Okay. And in fact, it is Kunz and Walby followed by explicit demonstration of these derivations in Patil Singh's paper of 1990. And then comes the E equal to 3 case. Again, the question is, what can you say about mu P and mu dark A? Oh, remember, we still do not have any assumption on these integers m0 to me minus 1. Still, they are arbitrary. The moment you assume certain things like almost arithmetic, etc., you start getting more definite results. But in general, up to E equal to 3. Now, this is a very interesting result by Moe in 1979, where he actually demonstrated, he gave a family of space curves, for which mu P is unbounded, but that is not a monomial curve. Okay, so that does not have a monomial parameterization. So, or rather, that is not given by a numerical semigroup, right? Okay, so therefore, in this case, mu P is unbounded, but not the monomial situation. But in general, the question is what we have asked here. For that, this answer is actually, well, it is not true that you always have a bound. You can create families for which it is unbounded. And then this is a result in that paper. They showed that for the same family, the mu of dark O is also unbounded. Okay, so this is the story up to equal to 3, and for e greater than or equal to 4 also, same things don't get any better. In fact, you do create a lot of families for which mu p is unbounded and mu dar q is unbounded, etc. Okay. Okay, so now comes more definite cases, that what I have said just now, that if you have a situation, if you assume that the integers, they are spatial in the sense they are almost arithmetic sequence, what does it mean? That means at most one is is not behaving well, but the rest of them, e minus one of them, they are forming an arithmetic progression. Then this is the result that they have proved, that e being the embedding dimension. So for a given e, this mu dar ko and mu p, they are bounded above by this beautiful polynomial functions of e. Okay, so this is a very interesting phenomena. So at least for these situations you do have. So in effect, it actually says that, you know, mu p or mu dar ko, they actually tell you, what exactly do they tell you in terms of the numerical semigroups? If I go back to the numerical semigroup situation, then you will soon see that this actually tells you that the ideal IS, according to the notation of Professor Herzog, this is basically your mu IS, and this mu dar ko is basically the cardinality of the pseudo-Frobenius. Okay, so this you will see why it is the pseudo-Frobenius very soon. Okay, and then the 1993 paper of Patil, where he actually gave an explicit calculation of this mu p for under the assumption that m0 to me minus 1 form an almost arithmetic sequence. Now here is I am kind of deliberately I have mentioned it here. Now this happens to be the first Betti number of O, because see, there is also the very natural question which obviously comes, that what can you say about the free resolutions, about the Betti numbers? Is it possible to compute them? Is it possible to give a bound? Because this bounds on mu p and bounds on mu dar ko essentially happens to be, in this case, the bounds on the minimal number of bounds on the first Betti number, and mu dar ko actually gives you the bound on the last Betti number. So this is the interesting thing, that there is some you can say that there are some homological things also associated, but always the proofs, at least as far as I know, always the proofs are like a very detailed investigation of the numerical semigroups. And if I may say so, it is in fact the Aperi set which tells you, which gives you the maximum amount of information. Okay. And then this was my work with him, where we could calculate the number very explicitly. And for the monomial curve O defined by the almost arithmetic sequence, that means when the numerical semigroup is generated by an almost arithmetic sequence. So, and then eventually this also gives you that, by type I mean the Cohen-Macaulay type, because you will see soon that why am I saying that it is the Cohen-Macaulay type? Why am I saying that it's the last Betti number? That is because of, maybe I'll take you to that theorem first. Yeah. So it is this result of Jürgen Traft, where it was probably yeah, so it is after his thesis perhaps. So this is the paper where he actually shows that the dar ko, the derivation module, the k derivations, is actually minimally generated by this set. And this is your delta dash, if you remember, this is your pseudo-Frobenius according to that notation of ours, right? So this is the pseudo-Frobenius. So therefore you can understand that now the pseudo-Frobenius you have just now heard in Professor Herzog's lecture is the Cohen-Macaulay type. And it is also true that for this kind of one-dimensional situations, you have the last Betti number giving you the Cohen-Macaulay type. So therefore, the mu of dar ko, if you subtract 1, that is the one coming from here, then you are actually getting the last Betti number, the Cohen-Macaulay type, right? So this is the theorem which kind of has a lot of impact, and that is what has been used. And detailed counting gives you exactly what the Betti numbers are, the last Betti numbers are, or which is of course coming from this result. Okay. And by the way, maybe since I am saying Kraft's observations, I should say this also, that actually here you do have this result, which is a very interesting result, that if you have a symmetric semigroup, then you have this very nice upper bound on the mu dar ko, but then boundedness of mu p is still an open question for arbitrary E for a symmetric numerical semigroup anyway. Okay. So, and then eventually, I started looking at the homological aspects or the syzygetic aspects, and this was the result proved with Philip Gimenez and Hema Srinivasan, that we could explicitly compute a minimal free resolution for the arithmetic sequence and in arbitrary dimension. I mean the m0 to me minus 1 when they form an arithmetic sequence. And the main work there was to show that it can be, this ideal can be written as a sum of two determinantal ideals, and then we could use the Egon-Northcott and the iterated mapping cone and some minimizing techniques. And then for the almost arithmetic, well, this is the only success story that I know that we could prove this with students of mine, that for e equal to 4, we do have an explicit resolution. But unfortunately, I do not have any spatial structure for in general. Okay, so now I would like to say something slightly different. So the question is, these are the remarks that counting the pseudo-Frobenius gives the type and the last Betti number of O as well, and knowledge of Aperi set is important. Now, what I would like to say that what is a current ongoing thought is, sorry, this is, yeah, sorry, I think this slide is repeated. Yeah, okay. So let us use this letter M for the multiplicity, that is the smallest non-zero element or the smallest generator, minimal generating set you may take. Okay, and then clearly your Aperi set with respect to M is going to look like this, because these are the elements congruent to I modulo M, and I is running from all the way from 0 to M minus 1. There are exactly M of them. So you can write them like this, where K1, K2, Km minus 1 are natural numbers, right? And now this, you have already heard this, that these KIs, these are exactly the gaps. So if you count them down, the total number, that is what is called the genus. So basically, you know, in a numerical semigroup from the Frobenius onwards, the conductor onwards, everything is there. Before the conductor, that means from 0 up to Frobenius, there are elements which are there, which are elements which are not there, that not there elements, they create the gap. And when these two numbers match, it is symmetric. Now the question is like, how you, of course, there are many results regarding gaps and the non-gaps, and you have already heard a conjecture from Professor Herzog's talk. Okay, so there are many things, but now what I'm going to say is the following. So for the calculation of the Aperi set, for the computation of the Aperi set, can we use this gap in a more effective way? So I would say an ongoing thoughts rather than ongoing work. So something that we are thinking with my students. So this is an interesting, so I would like to say it's an integer programming approach. That this is a nice observation by Residuals, which has been used in some other work also, that you can actually use these inequalities. And so this is basically the summation xi equal to g is also a constraint. And you are, now look at the last two lines, that last 4 lines rather, there is a 1-1 correspondence between the semigroups with multiplicity M and genus G, and solutions to the above inequalities where we identify the solutions K1 to Km minus 1. Remember, this K1 to Km minus 1 are the gaps, and then their sum is the genus with the semigroup that has Aperi set. So if you know K1 to Km minus 1, then you know the Aperi set clearly. There is no doubt about that. So these K1 to Km minus 1, I want to see them as a integral solution, rather, I mean, non-negative integral solutions of these, if I may call it a linear programming problem. But what you don't see is what is the objective function here, right? So this is exactly what is the challenge, and this is exactly what the thoughts that are going on, some experimentations are going on. So this is the function that we would like to optimize. And now in optimizing which sense? That's the whole idea. Okay, or rather you may take that if I know the M and the G, then this is summation xi I equal to 1 to M minus 1, where M is the multiplicity, minus G equal to 0. So I want to minimize certain objective functions subject to these constraints. Okay. Now, of course, I can convert it into an integer programming problem. I can throw in some surplus variables, the standard techniques. And you know that there is a Grosvenor basis technique for handling integer programming problems, and that is pretty good. So if I may write it in the standard form, if this is my objective function, a1, a2, an are being treated as variables, and suppose I have thrown in lots of slack variables, and this is my, these are the constraints equations, and I am looking for non-negative solutions, okay? And then this n is the total number of variables, including the slack variables, and the set of all n real tuples, those we satisfying the constraints is what we call the feasible region. But I am interested in the integer tuples, right? But well, this is the technique which people usually use, that you actually introduce a variable zi, and then you kind of write it like this. So zi, so which are the, how many zi's? M of them. Which m? So these m, there are exactly m many such equations, and throw in a zi for each one of them. So z1 here, z2 here, and then raise it to the power, okay? And then what you get is something like this, and take their product, okay? Now, why you are doing this is because this basically amounts to this kind of a situation, that if you have phi from here to here, and if this is your function, if this is the K-algebra homomorphism that you define on the variables, then this is an integer point in the feasible region if and only if phi maps to maps a monomial this to this. So you see, this now becomes a kind of a sub-algebra membership problem, if I say it in the language of computational commutative algebra. And then let me just show you that what we can do is that basically what we are trying to do is, if I may call these as fj's. So which are these fj's? These are these fj's. These are the fj's. Then basically what we are saying is that this subalgebra of the which is a subring, question is, this is definitely the image. Now you have some monomial over here, you want to know whether it belongs to the image or not. Well, this is also pretty much effective. There are effective ways to deal with this, okay? So what would be the effective way? Well, we can give this kind of a Grosvenor basis technique, that what you do is you take the, just like the elimination technique basically. So you take the big polynomial ring, and then you take this ideal, and then you choose your monomial order, in fact an elimination order, because what you want is that zi should be greater than any monomial containing only wj's, because you want to basically, you know how elimination order works. Whatever you want to eliminate, you kind of prioritize them. And then, well, these observations, these results, these are very standard results. For example, Cox Little O'Shea's second book using algebraic geometry gives you a very good detailing about such things. Then you can actually show that this is your, this belongs to the image, because that is what you want by the previous observation. Okay. Now, this is basically some thoughts that is going on, because what I feel is that this is certainly not the most efficient technique as far as computing is concerned. Well, in fact, I was discussing with some computer scientists, and they really showed, suppose you take a typical Fontaine equation approach, for example, what is implemented in computer algebra software like GAP, definitely that much faster, at least for some small examples, okay? But that's not the point. Point is, otherwise, if I'm trying to understand the Aperi set well, this could probably give a more clearer view that what kind of points in the, you know, I mean, it's kind of a better description, possibly. I can't claim it yet. There's possibly a better description of the Aperi set in terms of these integer points in the feasible region. Okay, and now my time is almost up. I'll just finish quickly. So this is another couple of things that if nothing to worry if your constraints have negative integer coefficients, because all you have to go that you have an analogous theorem for the Laura polynomial rings, and therefore you can have a similar kind of result. So that's not a problem to deal with. Okay, so now this is a couple of questions that can one have analogous formations for the Aperi set with respect to any non-zero element of gamma. See, here we are dealing with only the multiplicity. Here the Aperi set is with respect to m, but well, Aperi set with respect to other non-zero elements, especially the, especially when, if you are, for example, if you are studying projective closures, Cohen-Macaulay-Ness, it does matter, right? So these are the things. And also for the Aperi table, which gives you the good information about tangent cones. And this is the last thing I will say, that this is a theorem in Patil's thesis where he actually gave a generating set for the defining ideal in general. That means without any assumption on the MIs. And well, it definitely is technical. There's some technicalities. And this is what it has been extended to. So this, in fact, from that result, Patil could come up to a minimal generating set and things like that. And back in 2003, I could show that it is in fact a Grobner basis. And this is what a result by Brzezinski, Curtin, and Stuckrad, they call it a Patil basis. And in fact, they have a more generalized notion in terms of the row degree. And they in fact show that even that is a reduced and normalized Grobner basis with respect to a suitable term order. Okay, so I think I'll stop here and wish Professor Patil a very happy and successful life ahead. And thank you for your attention.
So thank you very much for your talk. Are there any questions or remarks? Nobody? Okay, so I thank you very much again.
Thank you.
And we have a break now, I think, for 15 minutes. And we will continue in 15 minutes with the...
I have a,
oh, sorry.
I have a question.
Yeah, okay.
Yeah, sure.
Yeah, my question was, can you characterize those semi-groups for which the Grobner basis forms a minimal set of generators of the defining ideal?
No, I do not know. I mean, this question actually has occurred to me several times, but I do not have a definite answer to this. Yes, in fact, when I was checking, see, the point is, even for almost arithmetic sequence, a good situation like almost arithmetic sequence, and under the nice standard monomial order, right, reverse lexicographic order, your minimal generating set may not be enough. So in fact, what I saw is that what we call Patil basis now, that whole generating set was in fact necessary to manage some more remainders. So probably that is very rare, but yes, but for several cases it did happen. No, I do not have any answer really.
Yeah, it's probably hard to say in general. Yeah.
Yeah, right. And also the question would be under some monomial order, so how to find that?
And if you use this this polytope that you defined, I mean, is it possible then to or maybe other people did it already, to give a bound for the semi-groups with given multiplicity and given genus?
That I think there are some results, yes. I think I have seen some results, but I don't think that's, I mean, probably not so much, the arguments are not so much using the polytopes. In fact, I don't know, maybe I'm wrong, but I have a lot of faith in this polytope technique nowadays, especially, you know, the notion of, in general, for say things like for affine semigroups and all, you have the notion of Hilbert basis, right? So, which is kind of, you know, there's a very serious analogy with what we are calling Patil basis. So probably understanding this polytopal, you know, the boundaries and things like that would probably give us better idea. So in fact, that was the reason why I started looking at it from this kind of integer programming approach. But I don't think there are much results using that concept.
I see. Thank you.
Thank you so much.
Okay, thank you very much again.
Yeah,
any more questions or remarks? Okay, so I thank you everybody, and then we will meet again 50 past the hour in India and 20 past the hour elsewhere. Okay, thank you.
Your mic is not there.
Yeah, so okay, this speaking thing.
Yeah, okay. You have two accounts. Yeah, we could hear.
No, but I don't see the sign, where is that sign for speaking or not speaking? Yeah, now it is there. Us now. Okay. You just put on your headphone. And I have to press this, right? Yeah.
So Venkatesh, can you hear me?
Yeah, now we can hear you.
Okay, good. And see me also.
Sorry?
You can see me also.
Yeah, we can see you.
So you also like Ramsey's theorem, right? Venkatesh?
Me? No, I never done those kind of combinatorics. But this numerical semigroup looks like yeah, it's good to know, like, because it has some connections with affine root systems.
Yes.
So if you want to study this regular subalgebras, so the corresponding root system will be closed. That will have this
I see.
part. Like,
That's good. Yeah. I think it's his thesis work.
yeah.
Of
I'm interested in learning more about that.
Yeah, that's an important paper. But Patil, I don't think saw that work. He independently was doing something. I think he saw it afterwards. You don't have a coffee machine?
In our department?
Huh?
Our department is very poor department.
Dilip,
Yes.
yeah, do you remember when we met the first time?
Chung,
Yeah.
Chung, yes, I remember. We were in Oberol Park.
Yeah. We are not invited. We were not invited.
But we were staying in down the hill there in some private house.
Yeah. I just look at the list of the participants of that meeting, of that conference.
Yes.
We were not on the list.
We were on the waiting list, I think, or
No,
when.
we come there illegally.
Yeah.
Professor Gurjar, you want to share your and check everything works?
Sorry,
You want to share your screen PDF file and then check?
but I can see it myself.
It is not shared yet.
Oh, it is visible here on my PC.
Okay. So there is a share screen in Zoom. It's in the green button.
Share screen.
Yeah, up arrow mark.
There are 3 buttons, 3 dots on the right hand side, right? Below.
Down.
Below.
Down.
Down there is a green button with the arrow showing up.
Where I cannot see it.
You see the down line?
Yes.
There is a chat and there is a participants and there is a record and there in between there is a share screen.
Oh.
Go to the Zoom app or Zoom website, wherever you are logged in.
The Zoom window, not your PDF.
Here, somewhere here.
Yeah, share screen.
Share screen. Yeah.
Yes.
Yeah.
Open your PDF file.
Is it okay now?
No. Not yet. It will come.
You have to.
Not yet. You haven't shared it. You have to click that and then choose.
To choose your file.
No, first open the file, the PDF file that you want to share. Keep it.
Just press on that screen where the file is.
The file is there now.
Yeah. Now
press on it.
Screen. Go to share screen.
It's a touch screen. Press on it. Otherwise, use the arrow.
Are you
Pop up.
Share. How to share this?
Share.
click on the share screen? Click on that button.
Share screen.
The button. And then you click on the file that you have opened. It will come as a small window there.
No, but they can't see it. That's it.
Understand?
Press on that. Let's see.
Are you using a desktop?
Okay.
Did you see the share screen button? Can you see the share screen button?
We press that, but
Then what is
After that, you press on the file. you
Don't you press
can
on
see
the
your
button?
file in a faint way.
You have to keep
Just press on that.
Yeah, then it will start sharing.
Once you say share screen, a number of screens come, and one of them is your file. 3 or 4 boxes will come, which is your files.
Buddhadev, when you click on share screen, does a separate dialog box appear? That should be the first step.
So once you click the share screen, you choose entire desktop if you are not getting any PDF files option. Choose entire desktop, then if you open your PDF file, that will be...
First open your PDF file. Only then it can be shared. First stop share, open your PDF file, then go back to share.
Okay, we can do one more thing. Can you send that file by this chart?
Take the file and share it from your end.
Actually, I see Buddhadev joining from his account. So possibly they are trying other system. Is that so?
No, they have...
Buddhadev actually has separately joined.
Oh God.
No, I think they both have joined off on the same PC.
Oh.
Because the camera appears same.
Yeah.
Your file as an attachment to an email.
Can you send the file to me? Then I can actually share it. If it is fine, then I can actually change the pages. Do you see chart box? Let me send message.
Which box? Sorry? Which box?
This chart.
Chat
I have
box.
sent message.
Chat.
Yeah, you can send the file to me. You can attach file.
Send your file to Venkatesh. How do you send it to Venkatesh?
The chat box is there, where you can actually
use the chat box. Okay.
In the chat box, you see the option everyone, and there is a small triangle there. Just click on that small triangle, you will see the name of various people attending the talk. From there, you just choose the person.
Sending my email, you can send it to that also.
Even that would be easier.
Just tell them I'm opening from another computer.
Okay. We are opening from using another computer.
Okay.
Yeah, fine.
Opening using another computer.
Fine, yeah, no problem.
So, Dilip, conjecture.
Yes.
Dilip, conjecture. No two Indians in the group here have met Chung at the same place first time. I met him in ICTP. You met him in Oberwolfach. JKV met him in Bombay, I think. What does Chung say to this conjecture?
You are muted actually.
I'm muted?
No. Professor Gurjar is muted.
I think it was not a good idea to change the computer. That is not, it usually takes longer. Computer always, there are some problems.
If they use the Linux machine, then it will create. If they use Ubuntu Linux, sometimes it will not show all these options.
Okay.
Because Zoom is more like Windows based. It should not create any issues. Yeah, now some screen sharing is coming, but nothing is coming.
That's right.
Buddhadev, if you can hear us, the system says that you have started screen sharing, but we cannot see anything. It's still a black screen.
Buddhadev can't hear. Buddhadev doesn't have headphones. He can't hear.
Oh, yes.
You can.
Let me message him. Just a second.
Why don't you call Buddhadev on WhatsApp or something and give a video demo?
Yes, yeah, I'm doing that.
Somebody can do it from here, I think. Oh, Adra left.
Okay, now sir, can you say something?
You just said something.
Hello, can you see me?
Yes.
Okay, all right.
But your screen is still not visible.
Video is not.
Your PDF file is not visible.
And the video is also gone now. I can't see.
This one or?
It's showing nothing. Your camera is not launched properly. It's saying. You have to just share screen, and then go to that down screen. Open that file. Is it now visible? Now visible.
Can you see the screen now?
No.
The blank actually. We don't
Oh.
see PDF file.
No, they cannot see it.
Can you send it by email? I can actually do it for you, and then I will change pages for you.
Can tablet? I have a tablet. Okay. No, Sarah also has a tablet. Okay. So can you try it from there? No, I'll get it working. No, I'm going to take it. Yes. Meeting editor over. Meeting editor over. Meeting ID. Meeting ID. Ah, here. 878 878 6291 6291 6766 6766. 120. Password code. COMM ALG ALG ALG. COMM ALG. Audio audio by computer. Then unmute and start video. Hello. Now video is on. So share. Where is the screen share? From browser it is.
I think we should interchange. Patil?
Yeah, that is also a good idea. You want to?
We give him some time. But
yeah, it will give them.
Martin, will you be ready?
Yes, I'm ready. No problem.
No problem. So where is
No
Gurjar?
problem whatsoever.
Gurjar?
Yes. Yes.
Can we interchange?
Yeah, sure. Yeah, sure.
Okay, let us do that then. Yeah, you'll get some time and you'll be able to project your talk. Okay? Yeah. So yeah. So Martin, may I request you? Martin, will you take the...
Yes. I share? Did you see my screen?
No, not yet.
But I shared it.
Yeah, we could see.
It is visible.
Okay.
We could see. No problem.
Your sharing screen has come, but your title is not come.
So now somebody else is sharing. Okay.
I heard somebody else is sharing. Oh, Gurjar is there now.
Okay. So.
Oh, I'm sorry. Gurjar, you have come somehow. I'm sorry, Martin.
No
the
problem.
Confusion. But in time to time, you can put it in. We'll just look at both. Okay. So, Gurjar, your screen sharing is ready. Are you ready?
Professor Gurjar, you have to unmute yourself. You are muted now. You please unmute.
First unmute. Yeah. Gurjar, unmute.
Unmute.
Yeah. Now we can hear you. And keep showing us your screen. And you can soon begin your talk. So let me introduce you. Everybody knows you. So I don't really have to introduce Professor Gurjar from IIT.
Okay.
And formerly from TIFR. He is going to speak on A1 fibrations of affine varieties.
Professor Gurdev. Okay, thank you very much for inviting me. It's a great pleasure on this occasion of Patil's retirement from IISc. I will just start immediately with mathematics because we have wasted some time. So let me start with the definition. We will consider algebraic varieties over the field of complex numbers only. So a morphism from a algebraic variety W to V, it's called an A1 fibration. If F is dominant, that means the image contains a dense open set, and general fiber of F is isomorphic to the affine line. That is the definition of A1 fibration. So let me quickly recall the definition of logarithmic polar dimension. So you start with some smooth affine variety, embed it in a smooth projective variety, such that the complement is a simple normal crossing divisor. So what it means for dimension 2 is that this divisor is a union of smooth irreducible curves. Any two irreducible components meet transversally and no three of them meet in a point. So let ky denote the canonical divisor of this compactification y. Then we consider the linear system h0 of y n times ky plus d. And suppose this dimension of this linear system is always 0 for all n bigger equals 1, then we say that the logarithmic Kähler dimension of x is minus infinity. So this was a definition introduced by Ithaka. Now, two basic properties of kappa bar are like this. Suppose you have a dominant map from a smooth variety x to another variety z, such that the inverse image of a general point is a finite set. So in other words, the map is quasi-finite. Then if kappa bar of x is minus infinity, then so is kappa bar of z. And in a special case of this is when x to z is a finite unramified map. So it is not only quasi-finite, but finite and unramified. Then kappa bar of x and kappa bar of z are always equal. This is a more general result, which I have not stated. So we start with a very important result due to Fujita, Miyanishi, and Sugie. They proved in 1979 that a smooth affine surface has log polar dimension minus infinity if and only if x has an A1 fibration x to c over some smooth curve c, which may be projective. It may not be always affine. So as the easy consequence of this result, they proved that the cancellation for C2 is true. Namely, if x cross C is C3, then x is C2. So this was a very important problem which they solved. Now, I come to some examples of A1 fibration. So it is well known that if you have a locally nilpotent derivation acting on an affine domain over C, then it is equivalent to giving an action of the affine algebraic group GA, which is just additive group of the complex numbers. So the way to get nice examples of A1 fibration, suppose you have a non-trivial locally nilpotent derivation acting on the coordinate ring of this affine variety X, such that the ring of constants, that means elements killed by the derivation, is a finitely generated C algebra. Then that corresponds to some affine variety, and it gives an induced morphism from X to Y. Then it's a fact that the general fiber of that map is A1. In fact, understanding these examples is very important in algebraic geometry. There is also a converse of this result, that when an A1 fibration can arise from a locally nilpotent derivation, but I will not go into that precise definition. Now, I mentioned that topology can be used in this study. So let me mention a result of Bialnicki-Birula from Poland. So for any complex analytic variety, you denote by HI CX the cohomology with compact support of X with coefficients in the group Z. Then Bialnicki-Birula proved that if GA acts on an irreducible smooth affine variety, then HIXC is isomorphic to HI XGC, that means the compact support, for I equal to 0 and 1. So here XGA is the closed subvariety of GA fixed points of X. And this shows that topology enters into study of GA actions in many ways. So this is just one illustration of that. Now I come to another important aspect of A1 fibration, namely describing singular fibers, because in general, the A1 fibration will have singular fibers. So suppose I have an A1 fibration on a smooth affine surface X. Then you can compactify X to Y such that this F extends to a P1 fibration F dash from Y to the closure of C. We say that a singular fiber of F dash is one where the fiber has at least two irreducible components. This is a very convenient definition here. So some important properties of this singular fiber of F dash is this F0 is always connected. F0 always contains a -1 curve. That means a smooth projective rational curve B whose self-intersection is -1. And if you have a -1 curve which occurs with multiplicity 1 in F0, then F0 contains another -1 curve. So you can contract such -1 curves in F0 successively and finally blow down F0 to a regular fiber of another P1 fibration on a blown down smooth projective surface. So using these properties, it is easy to prove the following result. So if F from X to C is an A1 fibration on a smooth affine surface, then every fiber of F is a disjoint union of curves isomorphic to A1, possibly occurring with multiplicities in the fiber. Now, I already mentioned connection with locally nilpotent derivation. So the result is that suppose F from X to C is an A1 fibration on a normal affine surface and the curve C is affine, then this arises from action of a locally nilpotent derivation on the coordinate ring of X, such that the kernel of that derivation is the coordinate ring of C. Now this result can be generalized to higher dimension also, but I will omit the statement. Now we come to singular surfaces, A1 fibrations on singular surfaces. So suppose you have a A1 fibration on a normal affine surface, which is not necessarily smooth. Then Miyanishi proved a very interesting result. The following assertions were most of them were proved by him. The first assertion is that every singular fiber of F is a disjoint union of irreducible curves isomorphic to A1. X has at most cyclic quotient singularities. Remember, X is now only normal, but its singularities can only be cyclic quotient singularities. And third is that if some irreducible component delta of a singular fiber occurs with multiplicity 1 in the fiber, then delta does not contain any singular point of X. So I just want to remark that I gave a simple proof of this using topology, and I proved the first assertion, namely the smoothness of all irreducible component, which was not proved by Miyanishi. Now there are also some results of this type when X is non-normal, but I will not mention them for lack of time. Now we'll go to higher dimension. What happens in the higher dimension? So there exists three-dimensional smooth affine varieties X such that the logarithmic polar dimension is -infinity, but X has no A1 fibration. So that if and only if condition is only for surfaces. So the example of Dubulo and Kishimoto is as follows. So there exists a smooth cubic hypersurface S in P3 such that if you look at the complement P3 minus S, it has log polar dimension -infinity, but P3 minus S has no P1 fibration. And this fact is closely related to the following famous result, that P4 has smooth cubic 3/4 T, which are unirational but not rational. Now again, I'll come back to singular fibers, but when the variety has higher dimension. So now suppose dimension of X is at least 3, and X has an A1 fibration onto a normal algebraic variety Y. We want to understand what kind of singular fibers F has. So as a sample, I will just state the following rather important result. That suppose you have a locally nilpotent derivation on a smooth affine 3,4 X and take the quotient, that the quotient corresponds to the ring of constants. Then that gives a map from X to Y. So suppose C0 is a one-dimensional irreducible component of the fiber from X to Y, then that one-dimensional component is always A1. So the proof of this result is not so trivial actually. So now I come back to locally nilpotent derivations again. So you start with a smooth affine variety, but suppose it has many independent locally nilpotent derivations, independent in a very precise sense, but I will not go into the definition. So the very interesting case is when the number of independent locally nilpotent derivations is same as dimension of X. Even in this case, if the dimension of X is more than 2, then the structure of such X is not well understood. In case of X equal to 2, it's quite well understood. I will not go into the description. So I want to state two open problems in this connection. So first is that you start with a smooth affine surface, actually now again back to surface, whose integral homology groups are all trivial for I bigger than 0. So such a surface is called as a Z homology plane. They are very important in affine algebraic geometry. And suppose I have a non-trivial locally nilpotent derivation on the coordinate ring of X. So again, you take the kernel of delta. It is well known that the kernel is a affine domain. It is finitely generated. But the question is whether this affine domain is regular. This problem is open for last several years. After many people have tried, but so far there is no success. What one can prove is that this, I should have said, I'm sorry, I should have said that the quotient, not X, it can be proved that the quotient has at most one singular point and it is of E8 type. So this much is known, but then how to get rid of the singularity, it is not clear. Second important question is, you take smooth affine contractible 3/4, and suppose it has 3 independent locally nilpotent derivations. Is it isomorphic to C3? So this is another unsolved problem which is rather important. One reason is that so far there is no good characterization of C3 in terms of geometry or algebra. There are some partial characterizations which are not very satisfactory. So one wants to have a nice criterion. So this is one of the questions, that if this contractible affine 3/4 has 3 independent locally nilpotent derivations, is it C3? So I want to just mention that recently Miyanishi, Masuda, and myself, we have written a book called Affine Space Fibrations, which has just appeared by Degreiter Publishers of Germany. And this book also deals with, of course, about A1 fibrations, but also there are many results about A2 fibrations. And the book is largely based on the research work of my collaborators, Marius Koras, Kayo Masuda, Miyanishi, Peter Russell, and myself over the last 35 years. So the book is written so that even non-experts, but somewhat advanced students can read it. Thank you.
Excellent. So thank you, Professor Gulzar. And I'm happy the book has come out right in time.
Yes.
And is it available in India or?
Not yet. Actually, I have myself not received the free copies yet.
Oh, okay. So I hope you also make an Indian edition at some time.
Yes.
Okay. I will now open it to the audience. Are there any questions to this talk? He has given a lot of information.
Hello.
But they are difficult.
Hello.
So, Vanishing, you are having
Yes,
some question? Yeah.
Sir, I want to know what is the definition of independent derivations. Means, can it be told in few words?
Yeah, okay, okay. See, a derivation is roughly like a vector field. You know, at every point you have some kind of tangent vector. So independent means if you take a general point on the variety and you have delta 1, delta 2, etc., then you have tangent vectors corresponding to each of the delta 1s, etc. Then these tangent vectors, they are independent in the vector space at that point, basically. Suppose it's an origin, then you have these tangent vectors. They should be independent in the corresponding vector space. So this should happen at a general point on the variety. That is the definition of independence.
Is it same as saying that the derivations are linearly independent? Like, if any LND is a derivation, so we can think of them as elements of model of differentials, and then they are linearly independent there. Is it same as saying that?
No, no, it is not same as that. No, no. I think this stronger definition which I just gave has to be given. We can also give in terms of you take successive rings of constants. Okay. So take modulo the first one, then you will get some affine domain. Then on that the second one acts. Suppose. So this transcendence degree should keep dropping every time. This is another way of saying, roughly.
But the second derivation may not restrict to the first.
Yeah, so I'm just assuming, for example, they were commuting.
But commuting, I think the result is no. That is clear.
Yeah.
So
in the precise definition was in terms of tangents I give.
Okay. So what is the difference between this A1 fibration and a cylinder like open set? In your definition of A1 fibration?
And what?
Miss A1 fibration is not that you are assuming all the fibers are A1. You are assuming
No.
General fiber.
General fiber. Yes. Yeah.
So is it not seen as existing of an LND?
No. In general, not, because the base, you take the coordinate ring of the base, it should be inert in the coordinate ring of the ambient space. That is a necessary condition.
Okay.
And sufficient also. So inertness of the base ring is necessary and sufficient. I didn't state that because it.
Or the existence of A1 fibration? Or?
No. Suppose you have A1 fibration from X to Y, where X and Y are affine. Then the coordinate ring of Y, suppose it is inert in the coordinate ring of X.
Okay.
Then this comes from a GA action or locally nilpotent derivation. Yeah.
Okay. That's a very simple. Thank you, sir. Very nice.
Okay. Thank you.
So, any other question or problem? You want to pose in a question? So,
I have already given 2 research problems for you.
Right. But you were going to say something about Patil, I thought.
But is there time? Is there time now?
I'll give you 2 minutes.
Okay. So, Patil and I have, we have been friends since 1979. When I joined TI as a postdoc and Patil was doing his PhD. And we were always interested in derivations very much. So Balwant Singh Patil and myself, we used to discuss derivations quite often. And after he went to Bangalore, I visited Bangalore several times. So I remember at least 3 times I had, great hospitality in Dilip's house. Now, coming back to the most recent developments, Patil, my student Buddhadev Hazra and myself, we are planning to write a book on the ramification theory. This should be ready in another year, I think. So on this occasion of his retirement from IISc, I would like to wish Dilip and his family a very happy and healthy life.
Thank you.
Thank you very much, Professor Gujar.
And I hope you are staying longer a little bit till 6:30 or so.
Yeah, okay, yeah, sure.
Okay, then you can meet Balwant Singh.
Yeah.
Okay. So
Okay,
thank
sure.
you very much.
Okay.
Now we'll take a 1 minute break and then we start again.
Okay.
Will you be ready? Huh?
I am ready.
You're ready? Fine. Because
Yeah,
we have
sure,
a
no
lot of
problem.
time.
I can.
So let us
Now I go.
go to the next speaker, which is Professor Martin Kreuzer.
He has to share his screen.
Yeah, I'm sharing.
Your screen starting has started. And he is from the University of Passau.
Has used the same now?
Yeah, we can see the screen now. And he's going to talk on differential methods for zero-dimensional schemes. Martin, up to you.
So thank you very much for the introduction and thank you very much for
the
allowing me to speak here. So can everybody hear me? Yes?
Yes.
Okay, very good. So when I was invited to give a talk here, I thought what to talk about. And my first idea was to talk about recent papers with Dilip on the Burnside rings, but somehow this is the past. And now the view of Dilip should go to the future, what he can do now after the retirement, of official retirement, because that's, of course, the time when you can start working. And I looked at his previous work and I saw some old papers with Balwant Singh from 1983 and 84 on maximally differential prime ideals and differential condition on the normal cone. And thought maybe I can speak a little bit about differentials. And I think it's a topic that has continued to interest Dilip for many years. So I saw another paper in 2000 about Kähler differentials for affine monomial curves. And I think even last year he gave a talk in advanced training school on derivations and differentials. So I hope that this topic is of some interest. So let me show you what is on the menu. So first I will talk a little bit about zero-dimensional schemes and traditional methods of studying them. Then I will tell you about Kähler differentials and relation to the normalization. And then I give some recent regularity bounds for the Kähler differentials and some applications to some easy geometry. And this is joint work with Lin Tran and Le Ngoc Long. They're both from Hui University. Long is at the moment also my senior assistant in Passau. So let's begin with zero-dimensional schemes. As everybody knows, in my talks, there are always a lot of quotations which are supposed to be a bit funny. So you can teach an old dog new tricks if the old dog wants to learn. So let's see if we can teach this dog a few tricks. So I have the polynomial ring of a field of characteristic 0. And I denote it by P. It's k x0 up to xn. I use n+1 indeterminates because I'm working in projective space. I have a homogeneous saturated ideal I, and it defines a zero-dimensional scheme in projective space. So X, the zero set of I, is a zero-dimensional scheme. And the coordinate ring of the scheme is denoted by R. So this is P mod I. Of course, the coordinate ring is here a one-dimensional Macaulay ring. So there exists some homogeneous non-zero divisor. And since we have characteristic 0, we have infinite base field, we can assume that x0 is the non-zero divisor, so that our scheme is contained in the affine space d plus of x0. And then a traditional way to study such schemes is to look at the Hilbert function. So in each degree, you take the dimension of the homogeneous coordinate ring. And this is the ith value of the Hilbert function of X or of the ring R. And this is very well known how it looks like. It starts with 1 in degree 0 and then increases strictly until it reaches the degree of the scheme, which is in the reduced case just the number of the points. And the degree where it reaches this maximum is called the regularity index. So be careful, this is the Hilbert regularity index, not the Castelnuovo-Mumford regularity index, okay? So for instance, by looking at this Hilbert function, you can know already a lot about this scheme. So for instance, in the set of, if you have a set of points, and then you can, from this Hilbert function that at most Rx plus 1 of these points are collinear. And if the last two increases of this strictly increasing sequence of numbers are 1, then there's a theorem of Anna-Bigatti and Tony Ceramita, which tells you that precisely Rx plus 1 points of X are collinear. So this is not if and only if, but it is one way of seeing that there are Rx plus 1 points which are collinear. So this is one way to look at the Hilbert function of this coordinate ring. Another way to study this is the canonical module. So the canonical module is just the dual of the homogeneous coordinate ring. So the homogeneous coordinate ring, since it is Connicoli, it will be a free module over K adjoint X0. And then if you take the dual module and you shift it by 1, you get the canonical module of the ring. And the Hilbert function of the canonical module will not give you a lot of new information. It will be just essentially just the minus of the Hilbert function of the ring. So it will start in degree minus R sub X, and then minus R sub X plus 1, sorry, and then increase strictly until it reaches the degree of the scheme in degree 1. But from the structure of this module, you can also know some geometric properties of the scheme. For instance, in the case of a set of points, Tony Ceramita and Lorenzo Robbiano and I, we proved that the set of points has the so-called Cayley-Bacharach property, which is from a well-known geometric theorem. And it says that if you have a hypersurface of degree R sub X minus 1, which passes through all the points but 1, it automatically has to pass through the remaining point. And this is a very well-known geometric property, but you can also see it in the structure of the canonical module. If you look at the multiplication of the first non-zero degree of the module to the degree 0, then this bilinear map has to be non-degenerate. So here you have again some algebraic way of understanding some geometric property. So these are the traditional methods of studying three-dimensional schemes. Now the question becomes, well, are there other tools, or is there some information which is not available in this way? And so some years ago, I proposed to study Kähler differentials. So are they very powerful? What is your superpower? This was a question asked to the Iron Man. Well, and his answer was, I'm rich. Okay, so let's see if also Kähler differentials are very rich. And of course, most of you know that they are. So again, we have this zero-dimensional scheme in a projective space and the homogeneous coordinate ring R. And then we can take the multiplication map from R tensor R to R and take its kernel, which is an ideal J. And then we can take the module J mod J squared. This will be an R module. The two R module structures coming from the left and the right here, they will agree. And this module is called the module of Kähler differentials of R over K, or of the scheme X. Excuse me. So then this module comes together with a universal derivation map, which starts with the ring R, and it goes to the module and it sends an element F to the residue class of F tensor 1 minus 1 tensor F. And this is usually called dF. So this is a derivation, and of course it has the product rule and it's K-linear. So this module, you can also calculate it if you have the equations defining the scheme. There is a very natural formula how to compute this module. So the module for the polynomial ring, the omega 1 of the polynomial ring, is a free module of rank n plus 1. And the basis is dx0 up to dxn. And then you have to take this free module modulo the ideal times the free module plus all the differentials of the elements of the ideal. So ix times omega 1 plus dix. And that gives you, of course, a way to calculate. You can also formulate this as a short exact sequence. So you take the free module R to the n plus 1, and then you have to mod out the images of the partial f by partial x0, comma, partial f by partial xn, coming from the ideals of elements of the ideal. And of course, it is enough to just use the generators of the ideal. So there's a really easy way to calculate this graded module. And it has also a Hilbert function, which we then can calculate with the computer. So we just define it as usual. It is the Hilbert function in degree I is the dimension of the ith homogeneous component of the module viewed as a vector space over the base field. And this Hilbert function of the Kähler differential module, it can also be described. You know some things about it. So it is 0 up to degree 0. So the module starts in degree 1, with the residual classes of the x0 up to dxn. And then for large degrees, it has a constant value. And this is, so the Hilbert polynomial is a constant polynomial, and this we call HP. And the smallest integer from where on it equals this constant value, the smallest degree is again called the regularity index of this module. So the smallest number j such that the Hilbert function of the module in degree j I is equal to the Hilbert polynomial for all I greater equal to j. And this regularity index is greater or equal to the regularity index of the coordinate ring plus 1. And in fact, starting from this place, our x plus 1, the Hilbert function will go down strictly to reach this multiplicity or this Hilbert polynomial value. So the Hilbert function of omega 1 is a little bit different. It goes up strictly, monotonously up to some high value, then maybe it goes up and down for a while, but then starting from degree Rx, it goes down again until it reaches this Hilbert polynomial value. So the question becomes, of course, is this interesting? Can we infer anything from this these invariants of the scheme? And we can even generalize it a bit more and go to the Kähler differential M forms. And this means that we have to take the mth exterior power of the module of Kähler differentials. And this will give you the module of Kähler differential M forms. And of course, if you take the direct sum over all of these exterior powers, you get the Kähler differential algebra. So this will be a differential algebra. And omega 0 is the ring itself. Omega 1 will be the module of Kähler differentials and so on. And then you can also see that you can calculate these mth exterior powers. It's not difficult. Again, you just take the mth exterior power of the polynomial ring, which is again a free module with the basis, the usual basis, dx0, which di xi1, which dxim. And then you have to mod out the ideal times the free module. And then you have to mod out d of ix, which the omega m minus 1 of the polynomial ring. So here again, we have if you look at this formula a little bit, you can see the algorithm, how to calculate a presentation of the mth exterior power of omega 1, or also called the Kähler differential M forms. So also for this module, there you can show easily, there is a Hilbert function. So this is a finitely generated graded module over the ring R. So it will have a Hilbert function. It will have a constant Hilbert polynomial, and it will have a regularity index, which is again the smallest degree from where on the Hilbert function equals the Hilbert polynomial. And so now, why should we look at these things? I mean, is there anything, can we even hope to have any interesting information from these objects? So the first time I found something which gave me hope in this direction was this example. So I have the projective plane, say over the rational numbers, and I take 6 points on an irreducible conic. So any 6 points on any irreducible conic. And this is X and another set Y, which is 6 points on a reducible conic. For instance, here the Y, I took 3 points on the X axis and 3 points on the Y axis. Okay. So if you now compute the usual stuff, so we compute the homogeneous coordinate ring and the Hilbert function, then you see the Hilbert function is the same in both cases. Even you can go a little finer and compute the gradient-free resolution. So the gradient Betti numbers, and you will see again, everything agrees. So you cannot distinguish between 6 points on an irreducible conic or 6 points on a reducible conic by looking at these invariants. What about omega 1? Omega 1 still agrees, and you see here is the Hilbert function of omega 1, 0, 3, 8, 11, 10, 7, 6, 6, 6. So again, omega 1 doesn't tell you anything, but now if you go to omega 2 and you compute the Hilbert function, then you see there is a difference. So the Hilbert function of omega 2 starts in degree 2, and in one case it is 3641, and in the other case it is 3651. So there is a difference. There is some way of detecting that this Y is on a reducible conic by computing some Hilbert functions. So what is going on? And this is why I thought maybe this could be interesting new tool to study zero-dimensional schemes. Okay, so the questions that arise naturally are, what is the Hilbert polynomial of this scalar differential M-form module? Then what is the regularity index? Or if you cannot really find it, at least do you have a strict bounds for it? And then which geometric properties can you characterize using these Hilbert functions of the Kähler differential M-forms? So now I will talk a little bit about a few answers on these questions. Of course, this research has just started and will go on for a while longer, I guess. So let's just talk a little bit about normalization. So we have learned a lot. Darth Vader says you have learned much, young one. And then the young one says, well, you'll find I'm full of surprises. So maybe he has not learned so much. So let's see if we can learn something by looking at the normalization of our scheme. So we have the homogeneous coordinate ring. And then we can look at this homogeneous quotient ring. So this is the ring of all fractions A over B, where B is a homogeneous non-zero divisor. So this is the generalization of the full ring. I mean, it's the homogeneous full ring of quotients. And here in this setting, since X0 is a non-zero divisor and is our very preferred non-zero divisor, you can easily show that it suffices to localize in X0. So for these denominators, we can just take the powers of X0, and this will give you already the homogeneous quotient ring. And then we also need the affine coordinate ring. So as we said, we can assume that X is contained in the D plus of X0. So this is an affine space. And how do you get the affine coordinate ring? Well, you have to mod out X0 minus 1 from the homogeneous coordinate ring. So with respect to the generators, this just means you have to dehomogenize with respect to X0. And then it is not difficult to understand the relation between these two rings. So in large degrees, so starting from the regularity index, the homogeneous component of the coordinate ring, the homogeneous coordinate ring, is just the affine coordinate ring times the appropriate power of X0. And therefore, we can also now, since now we can localize in X0, and we see that the homogeneous ring of quotients is just isomorphic to the affine coordinate ring, adjoint X0, X0 minus 1, so some nodal. Sorry? Okay, so this is just some low-row polynomial ring of our affine coordinate ring. And then we can take the polynomial ring over S over this affine coordinate ring, and this will be a subring of the homogeneous ring of quotients. I denote it by R tilde, And it is not difficult to show that it's an integral extension of R. So this is not always the integral closure of the ring, but it is the integral closure, for instance, if the X is reduced. And now, so let's look at let's compare the Kähler differentials for the original ring R and this slightly larger ring R tilde. So R tilde is just S joint X0. So we know how to calculate the Kähler differentials for the polynomial ring. So you have to take the S joint X0 times dx0 plus the Kähler differentials of S and extend the base ring to Kx0. So Kx0 tensor omega 1 S. And this tells us also something about the Hilbert function of this R tilde. Namely, in degree 0, it is the dimension of omega 1. And then starting from degree 1, we have also this Sx0 times dx0. So starting from degree 1, it is the dimension of the omega 1 of the S plus the dimension of S. The dimension of S is, of course, the degree of the scheme. So this is just the number of the points in the reduced case, so to speak. So here, this gives you the very first little application. It is very well known that S is smooth, the scheme X is smooth over the field, and here in characteristic 0, this is the same as being reduced, if and only if omega 1 of S is 0. So here you have a quick way to check if the scheme is reduced. Now, about these regularity bounds, what can we know about the regularity of this module? And here we had this idea of comparing the coordinate ring R and this ring R tilde. And okay, I don't know why the sacrifice didn't work. The science was so solid. This is maybe the young people will know it is King Julian from the Madagascar movies. And let's see if our sacrifice works, or at least if our science is solid. So let's look at the homogeneous coordinate ring again and compare it to this ring R tilde. So in the homogeneous, in the Kähler differential module, if we go to large degrees, the multiplication by x0 will be an isomorphism. You know, I told you that it will have a constant Hilbert polynomial, and this non-zero divisor x0 will actually give you, in large degrees, will give you an isomorphism between one component and the next. And it's also not hard to see that this has to start happening from degree 2 Rx plus 1 on. And so the regularity index of omega 1 is less or equal to Rix plus 1. Okay, so now we have this inclusion of the ring R in this R tilde, and this gives you an inclusion of a map from omega 1 R over K to omega 1 R tilde over K. And our hope, and this also proved to be true, is that in large degrees, this would be an isomorphism. Like R going to R tilde is an isomorphism starting from degree Rx plus 1. And so maybe also in large enough degrees, the map between the omegas is an isomorphism. This would give us then a way to determine the Hilbert polynomial of this omega 1 R over K. And so the kernel of this map from omega 1 R over K to omega 1 R tilde over K is easily seen to be the torsion submodule of omega 1 R over K. So here again, we have this very favorite non-zero divisor x0, so we can describe the torsion as all the elements which are annihilated by some power of x0. And then, in fact, we can prove that for degree greater equal to Rx plus 1, the torsion is 0, and the map from omega 1 to omega 1 R tilde over K in degree I is an isomorphism. And therefore, we see exactly the dimension of omega 1 sub I over K in this high dimension, in high degrees, namely exactly the degree of X plus the dimension of the omega 1 S over K, of the omega 1 of the affine coordinate ring. So here you see that the Hilbert polynomial of the Kähler differential module is not always equal to the degree of the scheme. No, it becomes larger if the scheme is not reduced. And in fact, again, it is equal to the degree of the scheme if and only if the scheme is reduced. Now, what about omega m for m greater equal 2? So higher Kähler differential m forms. Again, we can calculate omega m for the ring R tilde easily, because R tilde, as we saw, is just a polynomial ring over the affine coordinate ring. And so there's a formula. Again, you have to take the omega m of the affine coordinate ring and extend the scalars to kx0 plus kx0 dx0 times omega m minus 1 s over k. And the canonical homomorphism from omega m to omega m of R tilde is an isomorphism in degrees greater equal to Rx plus m. So now in case m equal 1, we saw this already, but using the formula given in part A, I think it is not difficult to see that this holds true. And this gives you also a formula for the Hilbert polynomial of the Kähler differential m forms of a zero-dimensional scheme. So now the last question is, what about the regularity index? And the regularity index is less or equal to 2Rx plus m. And this bound is, of course, easily seen to be sharp. So we can know quite a bit about these Kähler differential m forms. And the final question that I wanted to talk about is, can we know anything about the geometry from this? And let's look at the points in the plane. So, you know, in the internet nowadays, people are pretty nasty, and they are the so-called haters. And whatever you do, they will always be against it. And when you when they see you walk on water, they say, well, it's because you can't swim. So let's try to walk on water anyways. So I have the homogeneous coordinate ring of a finite set of points in the plane, this section. And I have the affine coordinate ring, which is just the homogeneous coordinate ring dehomogenized. And then let's look at the first, say, non-trivial case, namely 3 points. For 3 points, you have 2 possible Hilbert functions, 1, 2, 3, or 1, 3, 3. And 1, 2, 3 happens if and only if the 3 points are collinear. And 1, 3, 3 happens if and only if they are not collinear. So here the geometry is determined exactly by the Hilbert function. You don't have to go any further. Now, if we go to 4 points, the situation becomes already a bit more complicated. So if you have the Hilbert function 1, 2, 3, 4, 4, this is of if and only if the 4 points are collinear. And if you have the Hilbert function 1, 3, 4, 4, 4, then there are 2 subcases. So then if the multiplication on the canonical module from the degree -1 to the degree 0 is non-degenerate, then you have a complete intersection of 2 conics. And otherwise, you have 3 points on a line and 1 point off the line. So here, to distinguish the 2 subcases for the Hilbert function 1, 3, 4, 4, 4, you have to use the canonical module. But still, no need to go any further than classical tools, say. Now, for 5 points, I think it is the first time it becomes a bit more interesting. So 5 points on the line, you can distinguish, just detect by looking at the Hilbert function. This is only if and only if the Hilbert function is 1, 2, 3, 4, 5, 5, 5. So that's easy. And otherwise, there are 2 further cases of Hilbert functions. So there's one which is 1, 3, 4, 5, 5, 5. And this means that you have 4 points on the line and 1 point off the line by the result of Bigatti and Chiaramita, which I told you about. Look at the last 2 increases from 3 to 4 and 4 to 5. So they're both 1. So it means that 4 of those 5 points have to be on a line and 1 point is off the line. And if you have this, if this is not the case, so if no 4 points of X are collinear, then the Hilbert function will be 1, 3, 5, 5, 5. Okay. And then that there are still, I mean, of course, here 1, 3, 5, 5, 5, this means there is 1 conic through the points, right? I mean, the Hilbert function of the polynomial ring is 1, 3, 6, 6, 6. 1, 3, 6, 10, and so on. So there's exactly 1 conic through the points, but now the question becomes, is this conic reducible or not? And X is contained in the union of 2 lines. And if and only if the Hilbert function of omega 2 is this one, 352. And if you have 5 points, no 4 of them are collinear, and also no 3 of them are collinear, if and only if the Hilbert function of omega 2 is 351, 0, 0, 0. So here the omega 2 is the first place where there's a difference between the subcases C and D. Excuse me. So this is the end of my little excursion into geometry of zero-dimensional schemes. But of course, it's never the end of the jokes. There's always one more. And fitting with the current times, I chose the following one: give a man a mask, and he will show you his true face. Thank you very much for your attention.
That's very nice, especially in this these times where all of us are wearing masks. But why did you stop at 5?
Sorry?
Why did you stop at 5? It gets difficult.
No, you can continue, but there are many, many cases. I mean, the cases just get out of hand.
Yes. Okay.
You can go for a while. I just wanted to show that, you know, to distinguish the different cases, you will also need the Kähler differentials.
Yeah.
I think.
Very good. So thank you, Professor Martin. Any questions from the audience? Very interesting talk. So if not, we'll proceed to the next talk. Is that okay? Yeah. Thank you very much. Dilip, you want to ask something? No. Okay. So we'll take a 2-minute break because we didn't take a break before this. And we'll start. We're just about 2 or 3 minutes behind time. I hope Professor Leslie Roberts will not mind. But let us start the preparation for the talk by screen sharing. So, Professor Leslie Roberts, I see that you're in the audience.
Okay.
Hi. Yeah. So, I just want to make sure that, so you have in this form, which is easier to, no multiplication required. Okay. So can everybody see it?
Let me see, what time is it? Well, it's not quite 7:30. I was wondering if you could change my name. I named my laptop Leslie, and Leslie Roberts or something. Leslie R might be more informative if you can change it.
I see.
Maybe Venkatesh, who is the host, can rename it to Leslie Roberts.
Okay.
Or just put R on.
Huh?
R.
I see.
Yeah, I'm trying to do that.
Must be my fault.
Well, it doesn't matter. I guess everybody knows who I am anyway.
Yeah, everybody knows who you are. I made a mistake, I think.
But I've come across this before, and it was too hard to figure out how to change the name of my laptop because I did something when I installed it, and that was before Zoom existed and stuff like that. Okay, so I've pretty much forgotten how to prepare slides, so I just have a PDF file, and
better actually, because you can see.
Okay, so is the talk officially starting now, or
in 2 minutes? I think. Right?
2 minutes. Okay, I'll wait for 2 minutes then, and then I'll start to say something about this.
So let me know if you are ready.
There.
You start at 5. 2 minutes.
2 minutes. That's wait a minute now. It's hard to tell for sure the exact time. You can tell me when to formally start. And then
Sure. This will not be the title of the paper, I'm sure.
I think Venkatesh was able to change it to Leslie Roberts.
Okay, so maybe I can start now.
Sure.
First of all, I'd like to thank the organizers for inviting me to give a talk. And okay, so first of all, I'd like to thank the organizers for inviting me to give a talk. And I'd like to wish Dilip well, although I'm sure everybody else will also. Okay, so my last paper with Dilip was also joint with Ping Li, who is my former PhD student with Dilip, and it was called Basis and Ideal Generators for Projective Monomials, and it appeared in the Commutative Algebra journal. Now I have, I won't attempt a literature survey. That's too, it's not so easy after a number of years to tell where all ideas came from. And I'll just refer to LPR as a source. And then Ping and I have a new manuscript, which so far hasn't gone anywhere. So I'd like to explain a few things. First of all, I want to say what a projective monomial curve of degree D in P3 is. Now you can define projective monomial curves in any projective space, but the case where we can do interesting things is P3. So we describe the curve by giving three integers A, B, D, 0 less than A less than B less than D. Now, in effect, there's always a 0 in there, but to just describe the curve, I just call it ABD. And we want the GCD of ABD to be 1. Then we consider the semigroup generated by D0, D minus 1A, D minus 2B, E, and alpha 3. Let K be a field. I don't think the field matters, but we can take it to be Q if we want to, or C maybe to be safe. And S and T indeterminates over K, and identify the semigroup ring S over K with the algebra K square bracket S equals this thing generated by monomials in S and T corresponding to the alphas. And let R be this, R a polynomial ring over K, and the map phi from R to K square bracket ST defined by the generators there. Then this is a surjective ring homomorphism, and the kernel of phi, which we define to be P, is a homogeneous prime ideal in R, and R over P is K square bracket S. Now there is actually a physical underlying curve, which we can take to be proj of K square bracket S contained in P3, and R is really the homogeneous coordinate ring of some projective embedding. And that projective embedding happens to be given by monomials. And now I'll just mention a few properties of the ideal P. P has a minimal set of pure binomial generators. Now, further consideration started out in the paper LPR. We divided the binomial generators into two types. And to get the definition so that things work out exactly, it's a little bit fiddly. But we define a type 1 generator if F does not have X0 in one term and X3 in the other. And a type 2 generator otherwise. So you automatically get two types just by the definition. So we can say what they are. Type 1 generators of the form X1 to the A1, X2 to the A2, contains one term of this form. It has to have a term without X0 and X3 in it, and it has to be a positive degree, but it could be that one of A1 or A2 is 0. And the type 2 generators must be of this form with A0, A1, A2, A3 all greater than 0. Now there are two homogeneities here. We have to have A0 plus A2 equal to A1 plus A3, And then you have to have be homogeneous in the powers of S and T. And I've suppressed writing that down. But if you consider the homogeneity requirements, they all have to be positive. And now if we factor it by both of them, then we get k square bracket x0 to x3 divided by p. And that's isomorphic to J1 for an ideal, which turns out to be monomial. So this is a first simplification. We've done something where we concentrate on monomial ideals, which are easy to deal with. And this yields a bijection between the type 1 generators of P and the minimal monomial generators of J1. And to capture the type 2 generators, we can factor out by x1 and x3. Now we could also factor out by x0, x2, and make it sort of a different representation. So k square bracket s factored out by s to the t to the d is this, and this k square bracket x1, x3 factored out by j2, and that's a monomial ideal in x0, x2. So now I had a bit of panic in that I was afraid of misremembering how this works. It turned out to actually be more complicated than I had thought. I'd sort of partially remembered because I haven't looked at this stuff for quite a while. And so this yields a bijection between the type 2 generators and some of the minimum monomial generators of J2. So I think that's correct. And a suitable G, there's some subtlety in that the set of minimal generators of P is no longer unique, that you can make some minor changes in the generators. And if you choose the right one, then you get a bijection between type 2 generators and some of the minimum monomial generators in J2. Now this, there are some complications that there might be some monomial generators of J2 that really correspond to type 1, so you have to be a little bit careful, and I've suppressed some of the details. But what happens here, and this is the key idea, it is that in the respective planes x1, x2, and x0, x3, the exponent vectors of the generators lie in the Hilbert basis of lattice points in a cone. And it might be better if I just scratch this out. The exceptions are the type of thing that I was talking about up there. They may not, you may be overcounting in the type 2 generators. They lie in the Hilbert basis of lattice points in a cone. And then this is the crucial part, which I'm not going to go into detail, hence lie on line segments, which can be calculated using continued fractions. So this gives us a method of calculating. And because of the shortness of the talk, I've suppressed some of the details on this. But what happens is we get a collection of vertices and a finite number of integer points between them. That's what the elements of the Hilbert basis are like. And then this permits a very efficient calculation of the ideal generators of P. Sorry? Was that a question or? Okay, so here, what I'd like to concentrate on is some of the consequences of this. And I have an example. I won't attempt to do the calculation, but for this curve 167, we have a segment of type 2 generators, which I listed, and we have 4 of them. And this is a segment because the exponent vectors lie on a straight line. And the key idea here in doing large cases is instead of listing all 4 generators, one can just give the endpoints and the number of subintervals, which is 3 here. 3 subintervals and 4 generators. So more generally, you can take S to be 1n minus 1n, and this has 3 type 1 generators and a segment of n minus 3 type 2 generators, yielding n generators in total. Now this has an enormous implication for computing. Now the calculations here I'm currently doing with Macaulay 2, and my claim is this is the largest possible number of generators for a projective monomial curve. So if n is larger, say 10,000, we will get a segment of 997 type 2 generators, and you really don't want to see them all. The endpoints and numbers of subintervals suffices to describe the generators. So that's the first key idea. And that you don't have to list all the generators. You can just put them in segments and give the number in each segment. So where are we here? Okay, so there are a number of properties of these things. Okay, so first of all, there are many characterizations of Cohen-Macaulay. And in our case, one, perhaps the simplest to understand is Cohen-Macaulay if and only if s to the d t to the d is a regular sequence in I guess, whatever ring the I guess a regular sequence in R. So then there are some properties here. A complete intersection is Cohen-Macaulay, that's well known. A non-obvious example, you just have to work out the examples, and some are Cohen-Macaulay and some are not, and there's no obvious way to recognize if it's Cohen-Macaulay or not. And here are some other consequences that we were able to prove. That a projective monomial curve in P3 is Cohen-Macaulay if and only if it has no type 2 generators. And the projective monomial curve in P3 is Cohen-Macaulay if and only if it has less than or equal to 3 generators. So some of these things were well known and appear in the literature, but in many cases we tried to give our own proofs anyway to fit them into the way we were thinking of these curves. So I think we left work with Dilip when we started getting into continued fractions as a means of computing. So these are some of the basic facts here. And then we can move on to more speculative things. And some of these things have partial proofs and mathematical arguments, and others just have some sort of experimental data that tends to support them. And the key one observation is that as the degree goes to infinity, the average number of segments of ideals remains small, possibly even less than 1, depending on how you count segments. There's some choices in how you count segments. And item 1 notwithstanding, the number of type 1 or type 2 generators can be made arbitrarily large if you choose the right or wrong curve. And a key question that sort of motivated our thinking about this is what happens to the fraction that are Macaulay? And as the degree becomes large, just experimentally, the fraction of curves that are Macaulay seems to approach 0.31, somewhere around that. And we did extensive computation. Let me see. Now we move on to the next page. In a table of ideal generators. Now we did lots of computation, and for higher numbers of generators, we grouped them, and I didn't put in tables like that, but you can compute quite large, for quite large degrees, the as long as you can do continued fractions, you can compute. And in degree 10 to the 7, where we could compute them all, although it took quite a while, the fraction that were Macaulay was 0.0012. And then this is the thing I claimed went to 0.31. And then another fraction had 4 generators, another fraction had 5 generators, and so on. So I think that was all the curves of degree 10 to the 7. And then there were too many curves in higher degree, and these were samples, and they tended to be about well, I've said 60,000 computations. I put them into what I call the standard sample. That's sort of an average of this, and this. So it looks like we started to try to do samples of size 20,000 in each of these degrees. And the numbers look remarkably similar. So of course this doesn't prove anything, but it does suggest that there is such a limit, and the suggestion is that there's a limit as the degree goes to infinity, and you get numbers something like this. Now, you can continue indefinitely, and the bigger the degree, the further you have to list up here, and you can't list them all, you just group them and add other tables. Now, another suggestion is that the median number of generators is 5 if the degree is sufficiently large. So if you pick a curve, project a monomial curve in P3, sort of at random, you get quite a few where the number of generators is small, even if the degree is very, very high. And the median appears to be 5. And this is suggested by the sum of these two numbers being less than 5 and the sum of these three numbers being greater than 5. So that's not a proof, but it has been tested quite extensively. And I think, I can't remember the exact computations done, but the largest case where the median was 4 was a few hundred, and then in all cases considered bigger than that, it turned out to be 5. And I was able to do the computing up to about, was a few hundred. Yeah. And the preceding items 1, 2, 5, 6, notwithstanding, the average number of ideal generators goes to infinity as the degree becomes large. And this one I think I can actually prove by producing many examples of the type 1 n minus 1 n. So the number of generators there is extremely large, and you only need a finite number of them to push the, well, a finite number perhaps increasing with n, but for each n, you need a finite number of them, and you can get enough of them explicitly to make the average number of generators go to infinity. So this is basically the type of results we were getting. So let me just think about that. I've probably forgotten to say something interesting. Some of these things have partial proofs, and other things I have absolutely no idea how to prove. I indicated that 7 you can prove, but maybe not the precise number. This, I have absolutely no idea how to prove that, even though it's a very striking property of the behavior. And I have no argument to give these exact numbers, but I can sort of do approximate calculations that suggest there ought to be such numbers. So anyway, who cares? Well, I think computational complexity is sort of an honorable question. And the fact that this computation is equivalent to, is essentially equivalent to continued fractions, I think is interesting in itself. But if you want to know in more detail how things behave, if you can compute up to degree 100 or so, you might feel you've got a pretty good program. And I might mention that Macaulay 2 has a built-in program called Monomial Curve Ideal. And that sort of checked other computations up to where you could get the two to work. However, the Monomial Curve Ideal program was starting to fail at about 10 to the 5. And also it can't break the generators up into 2 types. So you get you're going to get your long list of thousands of terms if you pick the wrong example. And of course the computer will crash if you do too many. You have to be very careful. Now sometimes for comparing with Monomial Curve Ideal and my programs, you may want to show all the intermediate points, and there are variants of all computer programs that list all the intermediate ones too. But you have to be very careful that you can, with the modern computer, there's lots of memory and no limit, I think, on what Macaulay 2 can handle, except that it may run out of memory and the computation might take too long. But one can actually list all the ideal generators of curves of quite high degree. I don't remember quite high, but it can give lists of 100,000 or more in the versions I've been running. And So here a new issue arises. You just don't want to display that on the screen. That the length of time to display it on the screen can be many times longer than the actual CPU time. So there's some tricky issues you have to be very careful. But if you don't get up to a reasonably high degree, you can be misled. Like you might think that there are more complete intersections than there really are. And also in low degrees, there tends to be only one segment with a large number of ideal generators. And we actually never found much happening new beyond 10 to the 7, but one never knows for sure. And how high were computations actually done? At least on an individual example, it worked at about 10 to the 10,000. And I guess the title "Who Cares" really depends. Who cares about a curve degree 10 to the 10,000? But I think there's more of a case for caring if you go high enough degree to see all the phenomena. Now, also, knowing the complexity of a computation is always of interest. Now, this is sort of getting into very technical stuff that neither Ping or I was very familiar with, but the suggestion is the appearances of the complexity of the computation. You expect the complexity of the computation to be as large as the answer, but if you describe the generators using segments, the complexity of the ideal generation problem for curves, monomial curves at degree D and P3 seems to be a small power of log D. So if it's 10 to the 10,000, the measure of the complexity would be 10,000, or you might have to cube it because you get into issues about what do you count? Do you count the number of steps? Do you count take into account that the integers are getting longer, getting larger? And also there might be space limitations depending on the computer. And we felt on very shaky ground here, but anyway, that's where things stand now. So are there any questions?
So, what kind of machine is this?
I sort of heard a question starting to appear, but
yeah. So, on what kind of machine computer were you doing?
Oh, I was. Okay, so I'm running. Okay, Macaulay 2 is sort of. They don't seem to have a proper Windows version of Macaulay 2, so I'm actually running Macaulay 2 remotely on a Queen's computer, which is a Linux computer.
I see.
And that way they can easily update Macaulay 2. It just takes the computer technician minutes to do each upgrade, so I can always use the current version. Now I have Windows versions that are too old.
But you're expecting something, otherwise you won't do so much.
I'm sorry?
You're expecting something. What are you expecting?
I didn't quite hear the question.
So much, then what are you expecting?
Oh, what do I expect? I don't know.
No?
Let's turn the volume up here. Well, what I expect is sort of the numbers that I've listed in the table above are sort of observations, and I expect that if you go to higher powers, you just get similar numbers. That's the expectation, and the question is, what can you prove, and what's a reasonable thing to try to prove, and that I don't really have an answer to.
Okay.
Like I indicated that one can prove this. I think we can prove 7, 6. I have no idea how to prove. And again, I have no idea how to get the specific numbers, but they seem to be remarkably stable to me. And I've called something a standard sample. And in fact, several standard samples have been computed, and you get similar numbers with them. So that's the issue there.
So, any questions? Vinay?
Okay, so if there are no questions now, I think I have a few minutes where I could show a few pictures of Dilip, if that's all right.
No, but Vinay?
Stop the, sorry?
No, there is one person who might have something to ask. I'm wondering if he's still there. Vinay what? No, he seems to have gone. All right. So any other questions?
Well, you can always email me if you have a question. And
yeah.
some of the background information with more detailed arguments may be posted eventually on the either Ping's website or the website of the conference.
Interesting. Yeah.
And certainly these will be posted. I'll certainly send these to the organizers. I might make a minor correction on some of these remarks here that weren't quite right. But,
nice, yeah.
Yeah. So I'd like to stop the recording now and show a few pictures. I have to find my picture. Okay, so somebody said recording stopped, so that should have done it. Now I have to find my computer program, find the right program, which I should have started beforehand.
You have to stop share.
Oh, don't stop the sharing though.
What happened?
No, you have to share.
Okay, so is screen sharing still working?
Yeah.
Yes, it says I'm screen sharing. Okay, so here's a picture of Dilip, and I almost certainly have many such pictures, but I didn't have time to look for them. But oops, I don't want to stop sharing yet. So anyway, this is Dilip at a one of Tony Jaramita's after seminar dinners. So I don't know who this fellow is. I didn't want this sort of recorded because who knows who these people are. Do I want this on a recording? And there's Tony Jaramita, who Martin Kreutzer mentioned, joint work with him, and he unfortunately died a few years ago. But anyway, there's Tony, there's Joan. This was a master's student of mine at the time, I think. And I don't know who this woman is. I think she was a student of David Waylau. And my notes say who this person is, but I don't remember him. So I'm just showing this because I noticed Martin speaking before me, and he was talking about work with Tony. So I thought that would be interesting. And also Dilip is at Tony's dinner, and I think Dilip is just back over here, and Tony is here. So, and there's Dilip leaving. And let me see now if I can find where,
very nice.
What date this was. I tend to lose track of when pictures happened and everything. Okay. So
how many years?
now Dilip is leaving this morning. It's likely 5:25 a.m. and this was it looks like when was the picture taken? Well, it wasn't taken in 2021. That was when I did some tinkering with it. Yes, it says the original date was, it looks like October the 3rd, 2007. And the seminar was October the 2nd, 2007. So it looks like Dilip had to leave to go back to India the morning after the seminar. So that's
when you left.
I think that's all I have here.
Okay.
So you can,
thanks for sharing.
You can stop sharing.
Yeah.
I'll stop sharing, but I should still be, I don't want to leave conference yet. So I'll stop sharing and I'll also mute myself shortly, and then you can just continue, I think, with the next person who's doing it.
But that's the year around which Jaramita left, right? And went to Italy. You know. Wasn't Tony leave around that time?
Oh, was that a question addressed to me?
Yeah. When did
Okay, so what was the question again?
When did Tony leave and go to Genoa?
I don't know. I'm having trouble. I'm having trouble reconstructing the past history. The history is mostly in slides, and the slides for the interesting things are going to be 15 years old, and it's hard to find things.
Right. Okay. So I guess I should now give the floor to the main organizer, Apurva Khare.
Hello. Yeah, sorry.
Apurva.
I don't know if
We are a little ahead of time.
Yes, I know. Well, yeah, just about 1 minute ahead of time. So let me thank all the speakers and all the session chairs for a very nice first day of the conference. We will continue the talks tomorrow, I guess, at 10 a.m. There are 4 more talks in the second day. And for now, yes, the plan was to have Dilip say something in about 10 minutes time, but I don't know. Do we want to start early, or we can take a 10-minute break and then come back for Dilip? I mean, take a 10-minute break as in we can still stay here and chat informally. What do you think, Dilip? Would you?
Is it okay with me anytime? I mean, it depends on.
But Balwant Singh will not come.
He said he would not until 6 o'clock for sure. Yeah, not for this session.
He won't come before 6.
So there is another meeting link for that.
For that one is a different thing. That link, I think, is emailed separately to people. But
Dilip, may I tell a short story?
Sure.
Great.
We remember one time in the 80s or so, we went to Eastern Europe, I think to Prague, and you remember?
Yes,
and there was a conference, and when you went to Eastern Europe, you could buy nothing valuable at that time. The only thing what was really good was sheet music, which was not so expensive. So I wanted to buy some sheet music for my daughters, Mozart, Beethoven, such things, which are very expensive in Germany, but cheap there. But when you wanted to change money, this was really terrible because the official change rate was impossible. I mean, has nothing to do with reality. So the only way was to change money on the street. But I had not the courage to do it. So I asked you.